Mesdames et messieurs, bonjour à vous toutes. Bienvenue sur ce forum européen du bas carbone, de la mobilité bas carbone, deuxième journée ici à Pau, au pavillon des Arts, où nous sommes très heureux de vous retrouver pour également toutes les personnes qui nous suivent en streaming. Deuxième journée consacrée à une session technique et scientifique organisée sur la base d'un appel à contribution et d'une publication d'articles sélectionnés par un comité scientifique présidé par l'IFPEN et un jury de personnalités européennes expertes sur ces thématiques. C'est justement Florence DELPRAT-JANNAUD, présidente du comité scientifique, directrice du Centre de résultats produits énergétiques IFPEN, Académie des technologies, et présidente du club CO2 qui va nous rejoindre maintenant pour présenter l'intégralité de ce panel technique et scientifique. Madame, bonjour.
Bonjour.
Bonjour, merci. Avec 5 présentations que vous allez effectuer ce matin, je vous laisse présenter et suivre l'intégralité de ces sessions et de ces présentations.
Je vous remercie. Bonjour à tous. Donc tout d'abord, je tiens à vous remercier les organisateurs de m'avoir fait l'honneur de présider le comité scientifique de la session technique et scientifique, un comité scientifique qui réunit Raphaël Bourroman, qui est professeur d'économie à la Paris School of Business, Anne Bouter, qui est responsable scientifique au GRC, donc au Centre commun de recherche de la Commission européenne, David Chiaramonti, qui est professeur d'économie, de l'énergie et de bioéconomie pour les pays MED et tiers au Politecnico di Torino, et Maria Georgiadeu, qui est experte principale à la Direction générale de la recherche, de l'innovation de la Commission européenne. Voilà, donc je suis ravie d'être parmi vous aujourd'hui. Vous avez suivi les sessions d'hier qui ont été extrêmement riches. Nous avons hier largement discuté des enjeux de la politique énergétique de l'Europe, et on le sait tous, elle occupe une place centrale en fait pour relever les défis environnementaux, économiques et sociétaux donc, du continent, avec évidemment cet objectif d'atteinte de la neutralité carbone à horizon 2050, qui est déjà un objectif extrêmement ambitieux, mais je veux dire encore plus, et de plus en plus du fait du contexte mondial, ça a été dit et redit hier, qui est quand même complexe et incertain. Donc on a discuté hier évidemment les piliers de cette politique énergétique que sont la décarbonation du secteur des transports, des différents du secteur des transports et le renforcement de la compétitivité économique. Les ambitions sont fortes, ça a été dit hier, le secteur des transports, c'est un quart des émissions des gaz à effet de serre de l'Europe, 34% en France en 2022, avec différents secteurs, le routier, le maritime, l'aérien, qui sont des secteurs qui disposent de plus ou moins d'alternatives pour se décarboner. Et ce qui est ressorti hier, c'est que, je l'ai dit, le contexte est complexe et incertain, mais on a tous une certitude qui a été largement partagée hier, c'est qu'une solution unique ne permettra pas de décarboner le transport, ni même d'ailleurs un seul secteur des transports. Donc on a discuté hier ce panel de solutions qui doit être mise en œuvre, qui doit être adapté, déployé en fonction des secteurs. Donc bien sûr l'électrique qui est en cours de déploiement pour le routier, mais on a vu hier, il ne pourra pas seul décarboner ce secteur au moins jusqu'en 2050. Les carburants alternatifs, donc biocarburants avancés, et électrocarburants, qui permettent de décarboner les parcs existants et aussi les secteurs qui sont difficiles à décarboner, encore une fois, le maritime et l'aérien, et puis l'hydrogène, dont la place est encore, questionnée, on va dire, sur le rôle de l'hydrogène pour décarboner les mobilités, donc à quelle hauteur on arrivera à utiliser cette énergie. Donc la neutralité technologique, elle a été promue, je pense, par tous les intervenants, donc avec des messages forts, pas de position dogmatique, mais un objectif commun qui est vraiment la réduction de ces émissions de gaz à effet de serre. On a beaucoup parlé décarbonation. Il y a un mot que je n'ai pas entendu, c'est le mot défossilisation, parce que bien entendu, quand on parle de carburant liquide, Il y a du carbone dans les carburants liquides. Donc en fait, décarboner c'est bien, mais il faut aussi défossiliser, c'est-à-dire avoir recours à un carbone qui peut être un carbone d'origine biogénique, qui est un carbone extrait du CO2 capté dans l'atmosphère par exemple. Et on a vu aussi hier l'initiative Tour d'Europe qui a été accueillie à Pau et qui contribue justement à cette approche de neutralité technologique. Donc neutralité technologique, c'est vraiment un message fort qu'on a entendu hier. Alors on a aussi entendu un certain nombre de projets qui sont dans les tuyaux avec un besoin d'investissement pour pouvoir les concrétiser. On a vu qu'on avait les technologies en France, en Europe. On a entendu les engagements des différents acteurs institutionnels, industriels pour accélérer en fait le déploiement de ces technologies. On a aussi vu un certain nombre de questions, de défis. Et parmi les défis, bien sûr, il y a l'accès à la ressource. Donc la ressource au sens large, hein, bien entendu la biomasse, l'électricité, l'accès à une énergie décarbonée. Mais on pourrait aussi parler du CO2, des métaux pour les batteries. C'est un véritable enjeu. Donc c'est un enjeu sur lequel on travaille, et les instituts de recherche en particulier travaillent. On a aussi parlé des analyses de cycle de vie, hein, c'est aussi un leitmotiv. Elles sont essentielles pour pouvoir évaluer les différentes technologies. Et bien entendu, quand on parle des analyses de cycle de vie, on va du puits à la roue. Je ne le redis pas, ça a été dit, redit hier. Et puis on a aussi partagé le fait que la décarbonation, ce n'est pas une contrainte, hein, c'est aussi des opportunités. Et donc, je l'ai dit, il s'agit de décarboner, de défossiliser, parfois de décarboner, parfois de défossiliser les différents secteurs du transport. Et ça, c'est un levier pour accroître notre souveraineté, notre indépendance stratégique, réindustrialiser les territoires et créer des emplois. Donc, ce qu'on vous propose aujourd'hui, avec le comité scientifique, eh bien, c'est de faire un état de l'art, mais aussi des perspectives dans le domaine de la défossilisation et de la décarbonation des mobilités. Et donc, on va avoir une série de 5 présentations qui vont adresser les enjeux de disponibilité des ressources, les enjeux d'analyse comparée en analyse de cycle de vie et de compétitivité économique de l'Europe. Et puis, évidemment, à chaque fois, on aura des leviers, on mettra en avant des leviers pour accélérer les décisions d'investissement pour les différentes solutions technologiques. Voilà, donc je vous propose d'ouvrir cette session technique en abordant le sujet de la disponibilité des ressources. Et je suis ravie d'accueillir, je ne le vois plus, si je le vois, je suis ravie d'accueillir Abinash Ramasary, qui est cadre scientifique au Concawe en Belgique et qui veut nous partager donc, sa vision sur la disponibilité durable de la biomasse dans l'Union européenne à horizon 2050. Abinash, the floor is yours.
Great. Good morning, colleagues, and thanks for the opportunity to speak to you this morning. My name is Abinash Ramasary, and I am a science executive at Concawe. And the topic of my presentation this morning will be related to the availability of biomass resources in the EU up to 2050. As Florence has indicated, biomass resources are quite an important building block for the low-carbon energy transition. And one of the key questions that often arises is the availability of biomass resources, and this is something that I will elaborate on this morning. So maybe just to start off with a few words regarding Concawe, if you haven't heard about us. We are the scientific division of the European Fuel Manufacturers Association. This comprises approximately 40 member companies, which account for 95% of the European refining capacity, both of traditional fossil fuels as well as low-carbon fuels. Our mission is to undertake scientific research to support the energy transition, so both from a refining perspective, but also in terms of understanding the impact of our products on the broader economic cycle. One of the key areas of focus for us is understanding how refineries can support the energy transition, specifically understanding how can refineries support both the low-carbon energy transition as well as the transition of our conventional refining assets. The overview for the presentation that I will provide this morning covers different aspects. So the first one, I will provide an overview in terms of a study that was undertaken by us in 2021 related to the availability of biomass resources in the EU. This will be followed by a comparative evaluation of different biomass studies that were undertaken recently. And this will be followed by a discussion regarding the fuel outlook up to 2050 and whether biomass resources are sufficient to meet the forecasted fuel demand going up to 2050. And then lastly, I'll end with some key takeaways from the discussion. All right. So to commence, I'd like to highlight an important study that was undertaken by Concawe that was commissioned by us for the Imperial College of London in 2021. And this was specifically looking at the availability of biomass resources in the EU. As part of the study, we considered a number of different biomass resources, and these were primarily focused on the then RED II regulations, covering both the Annex 9A and Annex 9B feedstocks. So what you'll see on the slide is just a list of the feedstocks that we evaluated as part of the study. These comprised of a number of different agricultural residues, forestry residues, as well as wastes as well. So in terms of agricultural residues, as you'll see, we consider different types of energy crops, primary agricultural residues, secondary agricultural residues, as well as manure. In terms of forestry resources, we considered here stemwood, primary forest residues, secondary forest residues as well. And then lastly, in terms of waste, we looked at a number of different waste products, which included food waste, vegetal waste, municipal solid waste, sewage, packaging, paper, and wood materials as well. And then lastly, in terms of Annex 9B, we also looked at the availability of used cooking oil as well. This study was undertaken at a European level, so here we considered the EU 27 group of countries, as well as the UK at the time, and considered both scenarios for 2030 as well as 2050. And here we followed quite a top-down approach, where we looked at the overall availability of biomass resources, and then thereafter looked at current bio-based product usage for these products, and thereafter looked at the overall requirements for bioenergy, considering the different sectors, power, industry, residential, and then lastly, what would be left over then for transportation. As part of this analysis, of course, there are a number of different assumptions that were utilized, and in order to crystallize this, we evaluated different scenarios for future biomass availability. So these were the low, medium, and high scenarios. The low scenario considered biomass mobilization at 2020 levels, so considering farming, agricultural, and forestry management practices at baseline levels. And thereafter, in the medium scenario, we considered the opportunities in terms of increased mobilization of biomass resources by looking at increased mobilization in specific countries that have high biomass availability. And then lastly, in the high scenario, we considered further improvements in terms of farming as well as forestry practices, improved research and development in all of the European countries, and this, of course, results in a much higher biomass availability to 2050. What I'd like to share with you on the next slide is just the results of the study, and this is to give you an indication of where do the different biomass resources lie in the EU. So on the slide, you will see the different scenarios that we considered. Again, the low, medium, and high scenario for 2030 and 2050. And here you can see the distribution of biomass resources. The largest resources, of course, as you'd expect, are in the agricultural and forestry sectors, where we see a high proportion in terms of the potential for energy crops. And maybe to mention here, as part of our work, we evaluated only the production of energy crops based on cellulosic feedstocks on land that is considered unused, degraded, or abandoned. In addition, you'll also see here forestry biomass being quite high, primarily looking at stemwood, primary, and secondary forest residues. And what you can see here also is that bio-waste also contribute quite marginally towards the total availability, with the majority of the availability, as indicated, being in forestry and agricultural resources. When we consider then the biomass that's available for bioenergy, so here subtracting the biomass that would be already being used for existing bio-based products, the availability in terms of millions of tons of oil equivalent for 2030 is approximately 208 to 344, which then increases marginally to 2050 to 215 to 366 million tons of oil equivalent. So there we go. So here, now taking the basis of the total amount of biomass resources that is available in terms of overall bioenergy requirements, we then consider what are the needs of the other sectors that are using these biomass resources. So here, we considered a report by the European Commission, which indicated the use of biomass for power, industry, and residential sectors of approximately 170 million tons of oil equivalent. So based on this, we were able to then extrapolate the results and then consider what would be the biomass that would be available specifically for the production of sustainable biofuels. So here, looking at the best available technologies to be able to convert these biomass resources and then assess what would be the amount of biofuels that would be produced. And so what you'll see in the slide here is just the biomass converted then to final biofuels production for the 3 scenarios for 2030 and 2050. And here you can see the potential availability. And I think here it's important to highlight the potential portion here is that these resources are not necessarily at these levels today, and there will be significant mobilization that will be required to be able to unlock the resources to be able to achieve these levels of biofuels in future. So as part of the study, we then evaluated the production of the biofuels with the potential availability of approximately 29 to 79 million tons of oil equivalent in 2030, which increases then to approximately 32 to 137 million tons of oil equivalent by 2050. Great. So here I'd just like to also then take a broader perspective, comparing some of the other recent scientific studies that were undertaken in this space. Maybe just to start off with, I'd like to highlight an important study that we are currently still ongoing with, which was being undertaken with Utrecht University as well as TNO, where we are looking at biomass availability in the EU again, but here looking at a much more granular approach. So here, the intention is not only to determine biomass availability, but also understand the supply chains that are associated with biofuels production as well. So as part of the study, we looked at a more granular level at biomass resources, specifically using a spatial-based model to assess agricultural residues and understand the distribution of those resources at a regional rather than a country level that was undertaken in the previous study. So this study is being undertaken currently, and we expect to publish this later this year. I'd like to just maybe give you a snapshot of some of the results of the study, so you get an indication of the type of results that we're able to produce here. As indicated, we're able to map the agricultural feedstocks at quite a high level of granularity, and here you can see just an indication of energy crops, cereal straw, and maize stover up to 2050, where you can see the distribution of resources across the EU. As you would expect, energy crops are primarily, the potential is primarily in Southern Europe, which incidentally is, of course, the region where we see the highest amount of water stress. So here the key takeaway is as much as energy crops could be produced in these areas, there's a need to also account for the impact in terms of water usage as well. In terms of cereal, straw, and maize stover, you can see these are also traditionally based in the areas, of course, where cereal and maize is traditionally being cultivated as well. Just looking at some of the recent studies that have been evaluating biomass potentials, here I'd just like to highlight a couple of studies. I've mentioned already the Imperial College studies of 2021, the Utrecht and TNO study, which is still ongoing, which we published later this year, and then the recent study that was undertaken by DGRTD, the drop-in fuel study, was published in 2024. This is quite an important study as it also includes the new feedstocks as part of Annex 9, which are the crops grown on severely degraded land, as well as the interseasonal or cover crops as well. And then two earlier studies here for completeness as well as also the DGRTD study of 2017 and the earlier study undertaken by the JRC in 2015 as well. And what you can see here, of course, is that there's quite a big spread in terms of the results. And this, however, is primarily related to the assumptions that are utilized for the different studies. So the different studies use different assumptions regarding yield improvements over time, different assumptions regarding the amount of land that is available, and this results in the spread that you see in the results. However, what's clear from the results is that in general, from an order of magnitude perspective, you see that there is close agreement in terms of the studies, in terms of overall amounts of biomass that's available, given the nuances of the different study that I've mentioned. And also you can see, again, that there's a clear indication of the role of agricultural and forestry biomass resources that are contributing quite a lot in terms of the overall availability. Okay. Of course, one of the next questions to ask is what is the future outlook in terms of fuel demand as well? And how does this translate into the biomass resources that are available, and whether those will be really enough to meet the future demand? Florence mentioned a bit about the different needs for the different sectors. As aviation and maritime transitions, what will be the need of these different sectors, and how do we foresee this? So there was a study that we've also recently published. You can check it out on our website, looking at 2050 scenarios for Europe for decarbonization. This was a study that we'd commissioned with S&P Global Commodity Insights. The full report's available on our website, as I mentioned. And this specifically looked at what would be required to be able to meet the net zero targets of 2050. So looking at the role of both electrification and low carbon fuels. And here we considered two bespoke scenarios that were developed by S&P. The first scenario we called a max electron scenario, and here we looked at unprecedented levels of electrification across the road transport sector, specifically meeting the Fit for 55 targets, as well as the light duty and heavy duty targets, as well as some level of electrification in terms of passenger, in terms of aviation as well as maritime. The more molecule scenario here was a contrasting scenario which was derived from the max electron scenario, which considered a lower level of electrification complemented by the increased use of low carbon fuels. Here we did not consider the partial electrification of aviation and maritime till after 2050, and considered then an increased use of low carbon fuels being primarily sustainable biofuels and e-fuels in this scenario. What's of course important to mention here is, of course, these are not forecasts of the future, but really to say that these were two scenarios that we looked at to consider what could be the potential need for biofuels as well as e-fuels in future. There are a number of different future scenarios that could be considered as well, which of course within the constraints of time we didn't look at. So just to give you an indication in terms of what the results of the study were, from the work we were able to understand what is the future demand for the different segments, so light and heavy duty transport, aviation and maritime, and based on that determine the requirement for fossil fuels, e-fuels, as well as biofuels. Okay. So the next slide here just shows you what is the forecasted, or let's say the predicted requirements in terms of biofuels going forward. Here you can see a projection from 2024 up to 2050 for the two scenarios, the max electron on the left, and then the more molecule scenario on the right. And what you can see here, of course, is that as the targets for decarbonization increase quite steeply, the requirement for biofuels increases quite steeply as well. Here we map the demand for biofuels against those theoretical maximum potentials, which I showed you in the earlier slides for 2030 and 2050, approximately 79 million tons of oil equivalent by 2030, and 79 by 2030, and approximately 140 by 2050. And what you can see in both of the scenarios, as much as the requirement for biofuels increases, we do foresee that there will be sufficient potential availability up to 2050. And of course, here again, the point is that really this is a potential maximum availability, and there will be a number of different policy as well as strategic requirements to be able to unlock these resources. Maybe just to conclude with some key takeaways. First of all, just to highlight again that there is the potential for availability of sustainable biomass resources in the EU. According to our calculations, this is estimated to approximately 344 million tons of oil equivalent by 2030, which increases marginally to 366 by 2050. When we consider the needs of other energy sources, the remaining biomass potential can be converted to biofuels, and this results in approximately 79 up to around 138 million tons of oil equivalent up to 2050. As per the study we've undertaken with S&P, we foresee that this potential for biomass and sustainable biofuels will be sufficient to meet the demands of all of the sectors by 2050, considering the scenarios that we evaluated. To highlight the feedstocks again that contribute towards the availability, as I mentioned, low-grade stemwood, forestry residues, as well as agricultural residues and energy crops. Further, I think it's important to mention that as much as there's a potential for availability of biomass resources in future, there's a need to be able to develop the required supply chains to be able to unlock these resources. Of course, these resources are widely distributed and quite heterogeneous across the different regions, and therefore it's important to understand how to unlock these resources across the EU. And then lastly, just to indicate again that there have been a number of different studies that looked at biomass availability, and we foresee that there's quite a high level of congruence between the different studies, given the different hypotheses that they looked at in terms of mobilization of biomass resources. So with that, I'd like to say thank you and open up for any questions or comments from the audience.
Thank you, Abinash. Are there some questions in the audience? No?
Hi, Abinash. Just wondered if you addressed biodiversity needs. I know it's a question that comes up. Was that part of the study? Is there anything you can say on how you addressed that?
Yes, sure. So in terms of the feedstocks that we evaluated, one of the key requirements was that we needed to consider the impact in terms of biodiversity. So in terms of the specific feedstocks, we excluded land that was considered of high biodiversity value. You'll see the feedstocks that were considered here were specifically ones that we foresee that there isn't any impact in terms of biodiversity. And as part of the yield improvements that we considered as well for both agricultural as well as forestry, we also considered practices that are in line with sustainable practices to avoid impacts in terms of biodiversity. So I think, of course, one of the key questions that we often see arising is indirect land use change. So, of course, this is something to consider as well. So you'll see, again, as part of the feedstocks that we considered, the impact in terms of land use was quite strongly considered. And of course, here we, of course, follow the risk-based approach in terms of indirect land use change and only consider the feedstocks that were considered in, of course, RED 3, Annex 9A as well as Annex 9B.
Yeah, Sylvain Demour from Bioéthanol France. My question is about the limitations in terms of when you talk about availability. There is the owners of this biomass. Did you evaluate the willingness to put on the market that biomass? First point. And did you take into account the cost of mobilizing that biomass, which can be very, very different depending on the biomass you consider?
Sure. Okay, I will answer the second question, which is a bit easier. So to look at the cost to mobilize the biomass resources, this is part of the current work that I mentioned that we're undertaking with Utrecht and TNO, where we're specifically developing a model that evaluates the overall supply chain cost for biofuels. So considering both the farm gate, so to say, looking at the transportation aspect as well as the processing of the biomass. So here we're able to look at the biomass resources across the EU and be able to look at how much it would cost to mobilize those resources across the EU. So I hope to actually present this work later this year or perhaps in this forum again to be able to show you exactly the question, to answer your question in a quantitative way, how much it will take to mobilize those resources in different sources. To your first question regarding willingness, of course, that was something that we did not specifically look at, but I think it is an important aspect to consider. What would be the potential business models that would need to be developed to be able to unlock those resources, and what would be the necessary policy aspects that need to be considered to be able to encourage farmers and create incentives for them to do so.
Thank you very much. Unless you have a very... Oh, yes, Anne, last question.
Thank you, Abinash, for the great presentation. Anne Bouter, European Commission, Jersey. I was wondering, in the first slides, you presented from the study from Imperial College. For the three scenarios, did you consider also the environmental impact, for example, for the medium and high scenario? Because you say that the yields will increase. So I'm wondering if you increase the yield, then you will increase the amount of fertilizers and if you have some figures in mind, or if you intend to perform maybe a follow-up study.
Yeah, I think that's a very important question. I think I alluded to it a little bit in the previous comment as well. Well, you'll see that as part of the yield improvements that we considered in the study, they're actually quite modest. Approximately less than 1% per year. Of course, that accumulates over a number of years. But as part of that, we considered a minimization in terms of the impact in terms of the environment. So here would be minimization of the use of fertilizers, the use of pesticides, as well as more sustainable, as well as more precision-based farming practices as well. So this results in that the yield improvements are not as significant as you could expect when you obviously maximize the use of these fertilizers, etc. But we consider that this to be a more sustainable approach rather than to push yields at the detriment of the environment as well. Of course, this requires a lot more further evaluation as well. I mentioned a little bit about the crops grown on severely degraded land and the interseasonal crops as well. So we are currently undertaking a study at the moment where we'll look at this in more detail to understand what the impacts will be.
Thank you. Thank you very much, Abinash, for this very nice presentation, very encouraging also presentation. Thank you. On vous propose maintenant de poursuivre en fait sur ces enjeux de disponibilité des ressources en invitant Nico Weimer à nous rejoindre. Nico est titulaire d'un master en génie mécanique. Il travaille actuellement comme assistant de recherche à l'Institut des moteurs à combustion interne et des systèmes de transmission de l'Université technique de Darmstadt en Allemagne. Et donc, il va nous présenter sa vision sur la disponibilité d'essence durable et biogénique en Europe. Nico, the floor is yours.
Merci. Bonjour, Madame et Messieurs. And at this point, unfortunately, I have to switch to English because my French ends right here. I'm here replacing my colleague, Mr. Lars Knaup, and I'm going to talk about the analysis of the availability of sustainable biogenic gasoline in Europe coming from biomass. So let's have a short look at the agenda. First, we're going to consider the biomass potentials in theory, so the countries, the sources, as well as the boundary conditions. From there, we derive a technical potential, so we make some assumptions, we account for other uses. Then the biomass will be converted to sustainable alcohol. Here we have a look at production potentials as well as CO2 saving. And finally, we will convert the alcohol to sustainable gasoline. We'll talk about conversion pathways as well as production and CO2 saving potentials as well. But before that, let me shortly introduce the consortium who took part of it. The Energy and Bioproducts Research Institute at Aston University in Great Britain had a look at converting biomass into sustainable alcohol. The Institute of Technology at Hungarian University of Agriculture and Life Science had a look at the agricultural part as well, for example, energy consumption of harvesting, as well as try to give a little outlook of future developments of the agriculture, which unfortunately will not be part of those results yet. And finally, the Institute of Catalytics Research and Technology at Cultural Institute of Technology converted the sustainable alcohol to sustainable gasoline. So let's start with the considered potentials. We only looked at sources that are compliant with the RED III Annex 9, and we also considered only domestic biomass that is produced in Europe, and to prevent any discussions about interference with food supply, we only assumed second-gen biomass. So from there, we calculated a theoretical potential, which is the entire amount of biomass that is produced in the given area. And from there, we derived a technical potential, which considers the amount of biomass that is left after accounting for other uses, for example, heating or any others. We just included the demands of today. We're still working on future demand developments, so that will be part of probably a later version of it. So let's have a look at the countries we considered first. We covered a great share of Europe, but left out the Ukraine as a major contributor because of the unclear situation there. And the sources we considered are, first of all, agricultural residues, so mainly straw, perennial energy crops that are grown on marginal land, which I will explain a little bit later, forestry byproducts, animal feces, urine and manure, as well as processable waste. So let's start with the agricultural residues. So we assumed that the straw to grain ratio is similar for each crop for every country. We left out the use as animal feed fodder and mushroom production, as well as straw that is left or plowed into the soil to maintain the soil quality. So we assumed about 25% of the theoretical calculated potential can be technically used, which results in about 108 megatons of dry mass of biomass there. The energy crops on marginal land are considered as willow and poplar, so there's a huge amount of marginal land in the European countries and fallow land as well. So they are considered in the theoretical potential, but since fallow land is mostly left for a few years for the soils to recover and then recultivated with food crops, we left them out in the technical potential. So we only had a look at marginal land and tried to grow willow and poplar there. And we found out that 60% of the land is usable for willow and 90% for poplar. But since willow has the higher yield compared to poplar, we tried to maximize the part of the willow. So we assumed 60% of the land usable for willow and the remaining 30% for poplar, which results in a total of 174 megatons of dry mass there. So then the forestry byproducts. So we calculated the byproducts from wood production. So about 41% of the processed wood ends up as residues, split into sawdust as well as slabs and chips. And another 4% are lost due to shrinkage and other smaller losses. So you can say about 37% of the wood residues are available after accounting for already established bioenergy purposes, for example, electricity, for example, heating. And with this, you can say there's about 15% of the overall processed wood ending up in our calculations, which is about 17 megatons of dry mass. The animal feces, urine and manure part can be shortened because, as you can see, there's almost nothing left after accounting for organic fertilizers, so we'll keep it short there. And finally, the processable waste. When considering recycling, incineration, composting, and energy, you have about 8% left usable. But if you divert landfill waste and energy recovery waste to produce methanol, the technical potential increases to about 42%, which results in a potential of 25 megatons of dry mass. So in summary, we have about 325 megatons of dry mass per year of biomass technically usable. As you can see, most of them are coming from either the perennial energy crops or the crop residues, and the others are only minorly contributing. From there, we have to convert them into sustainable alcohols. So we took typical production pathways that are compliant with RED II Annex 5. The crop residues are converted to ethanol, as it's stated there, and all the others are converted to methanol. So from there, we have about 72 megatons of methanol and 22.5 megatons of sustainable ethanol to work with in the next step. Then, as I already mentioned, we convert the alcohol to sustainable gasoline. So we had a look at mainly two processes. On the one hand, alcohol to gasoline, and on the other hand, alcohol to olefins and oligomerization. The results you see are based on the calculations done by the KIT with the calculation software ASPEN Plus. You see an exemplary calculation with an alcohol feed rate of 1,000 kilograms per hour, and you see the outputs of mainly gasoline, but you see also see the byproducts, water, or depending on the process, LPG, fuel gas, or kerosene and diesel fuel as well. So in the last section, you see alcohol demand rate for every kilogram of gasoline. So how much alcohol is needed for gasoline? It will become important in a minute. We chose those two conversion processes either because the gasoline process are the obvious one, and the olefin and oligomerization processes are a little bit more flexible to produce not only gasoline but also other liquid fuels like, for example, kerosene. So now having the overall gasoline potential made from those alcohol feedstocks, as we already mentioned, depending on the process, you have about 33 to about 40 megatons of sustainable gasoline per year. I have to mention that the olefin and oligomerization processes are meant to be maxed out for gasoline, but they are flexible, as I said, and can be switched to, for example, produce more kerosene as well. So what about the costs? We have the share of the alcohol costs, which are directly influencing the overall fuel costs in the end. So as I said, the alcohol conversion rate directly feeds into the price. And obviously, the greater the plant, the lower the prices. A demonstrator plant on the left, 8,000 ton per year plant. With those, you have quite high prices, but if you're able to scale them up to industrial size, for example, a 1 or a 4 megaton plant, you can reach production costs that are similar to today's gas station prices. I know we're not talking taxation, we're not talking profits, we're just talking production costs here. And finally, let's talk CO2 reduction potentials. Here we also based all the calculations on the typical values from the RED II Annex 5 for crop residues and energy crops and the forestry byproducts, and we took into account another source to calculate the animal feces as well as the processable waste. And for comparative reasons, we took the fossil comparator of the RED II, which is 94 grams per megajoule. And you can see, depending on the pathway, you have about 78 to 84% of CO2 lowering there, but combining the ethanol and methanol pathways as well, you get about 80% for both pathways, the gasoline as well as the olefin and oligomerization pathway. But because the numbers are higher in absolute numbers for the olefin and oligomerization processes, the absolute saving potential here is higher as well. So let's conclude it. We found out that we can produce about 40 megatons of sustainable gasoline per year from those feedstocks, which is, to give an idea, about 49% of the overall fuel consumption in the countries we looked at in 2022. And we calculated about 79 million vehicles. For comparison, there are about 250 in the European Union. But you can fuel about 79 million vehicles per year with that. On my left, your right side, you can see a potential ramp-up scenario starting from today. You see the green dotted line. This is the biomass available. Obviously, the wastes are already available today, and it takes willow and poplar about 3 years to fully grow or to be harvestable. So we ramp up through year 2 and 3, and then we have full potential of the biomass available. The bigger problem is the investment or the scale-up of the production plants. As you can see, starting from today, we assumed that it takes about 5 years for a plant to be fully constructed or to be fully functional. So starting from today, the first plants will be ready in 2030. Which will result in a CO2 saving of 383 megatons of CO2 equivalent up to 2035, and then another about 600 megatons up to 2040 with full capacity and full production. But you can also see that there's a long-term market demand. For example, if you also consider the other purposes or the other usabilities for the biomass, for example, kerosene, when using flexible production pathways, and it does not interfere with the ramp-up of the e-mobility. They can go hand in hand and go for additional CO2 saving. So the earlier everything will be ramped up, obviously, the higher the GHG savings are. And as I said, the flexibility of the processes allows for different markets and applications, which gives investors a little bit more security to invest. Thank you very much. Merci beaucoup.
Thank you, Nico. We'll take some short questions. Jean-Baptiste et Anne. Le t'as levé la main premier.
Okay. Yes, good morning. Thank you very much. So you mentioned it was a question, but you already raised it. So the cost of production is a cost without any taxation. So the gap would be significant. But more precisely on your presentation, was it limited to Germany regarding the feedstocks? Because the fuel consumption, 80 million tons, according to me, it's the German and not the European volumes of fuel for cars or oil products. And the second one, in your feedstocks, did you consider the competition with biogas?
Yeah, thank you for the questions. Let me start with the first one. I think it's the fuel consumption in 2022 for all the European countries. So, yeah. Megatons. Did I say megatons or megajoule? Let me think. Maybe I messed it up. Sorry. Okay. Huh? Yeah, exactly, gasoline. That has to be mentioned, gasoline only.
So it would be diesel, gasoline?
We didn't, diesel is not part of it for the moment. And could you please repeat your second question?
Competition with biogas for the feedstock.
We are still working on possible interferences with other usages, especially in the future. These are unfortunately not part of the results yet.
Thank you.
Yes. Thank you, Nico, for the great presentation. Very interesting. Just wondering, on the slide, you mentioned that you use the red values, and you mentioned that you use the typical values. I was wondering if it was on purpose, or because usually in the red you find both typical and default values, and the default values, they have this safeguard increasing factor, and for regulatory purposes you have to use the default values and not the typical ones that you cannot use for regulatory purposes. So just wanted to know if which one you used.
Okay, yeah, we used the typical ones.
Thank you. One last question? No? Yes?
Abinash, I think.
Oh, sorry.
Thank you for the presentation. I think you talked about a little bit on your last slide, but maybe if you can highlight it. But I mean, I see there's almost a wedge here of opportunity for alcohol, for gasoline applications specifically, given of course the combustion vehicle ban in 2035. The demand for gasoline we anticipate to reduce quite significantly, and as you mentioned, the ramp-up period and commercialization of this technology to meet that. I do foresee that aviation will be a great sector to be able to utilize this, but maybe you just comment, because it seems almost like the window of opportunity is kind of closing a little bit on this pathway specifically for gasoline.
Yeah, absolutely. I mean, the scenario for that's why we at first just calculated for 2035 to, let's say, have as much gasoline potential as well left before there are no more new combustion engines, but you still have an existing fleet to cover, and that's where I think this becomes interesting again, because you can decarbonize the existing fleet even after 2035?
Okay, thank you very much. Thank you very much, Nico, for this very nice presentation. Je vous propose maintenant de passer à la thématique analyse de cycle de vie. Et nous allons accueillir Nicolas Kurtsoglou, qui est ingénieur chez Bioéthanol France et qui va nous parler de l'empreinte carbone de l'éthanol E85 100% pour les voitures essence. Nicolas.
Bonjour à tous. Merci pour l'invitation à présenter cette étude qui a été faite d'ailleurs par l'IFPEN et commandée par la filière du bioéthanol français. Donc Bioéthanol France, c'est l'association de tout... I will switch in English because there is no translation. I see Marco like that. So Bioéthanol France is the association of all the bioethanol producers in France, so Tereos, Cristal Union, Rocket, Vertex, which is just nearby, and recent alcohol. So I will present in the spirit of the CO2 neutral fuel definition a solution for petrol cars and hybrid petrol cars, which is E85 fully renewable, in which you replace the fossil gasoline with some renewable gasoline. So obviously, all of you know that, but many journalists keep talking about the ICE ban in 2035. Here we know that it is not exactly what is in the regulation today. In 2035, right now, it's battery electric vehicle plus vehicles running on CO2 neutral fuels, and the Commission was mandated to propose a definition. Now the revision of the regulation is going to be faster than the proposal of the Commission itself. So regarding CO2 neutral fuel definition, it's all thanks to Germany and the last moment discussion to include this CO2 neutral fuel vehicles running exclusively on CO2 neutral fuels in a recital. Basically, CO2 neutral fuels, the spirit is to say that the carbon they use is CO2 that is taken from, removed from the atmosphere, and that goes back to the atmosphere when the fuel is burned. So basically there are two type of way to remove the CO2 from the atmosphere, either photosynthesis with plants and biogenic CO2 for biofuels, or capture CO2 for e-fuels. Just a quick update on the political situation on this, the position of different member states regarding the first proposal of the definition. The usual words that she used to say, and all the other commissioners regarding CO2 neutral fuels, they used to talk about technology neutrality in which e-fuels will play a role, and since 3rd of March they talk about full technology neutrality as a core principle. And Stéphane Séjourné, who was asked on the 5th of March about will this mean that biofuels will be included like some member states asked, he just said that the question of e-fuels and biofuels will be put on the table of the European Parliament and the Council, and then the co-legislator will have to decide. So basically, when we are advocating for CO2 neutral fuels, it doesn't mean that we are against electric vehicles, and I guess like everyone here in Bioéthanol France and the whole bioethanol chain, we think that there will be a majority of battery electric vehicle, but there will be the need for other type of light-duty vehicles. And if we just don't do anything, it will be just fossil fuels in these vehicles. So the two first, blue and purple, it's more petrol type engines, and the three down, it's more diesel engines, so mainly for heavy duty, but still so, and they will probably be hybrids and most likely plug-in hybrids, so with low consumption of the liquid fuel, and running most of the time with electricity for daily So before going to the impact of the pollutants of the E85 fully renewable, just reminding that what is important for the climate change is just science. So science is what is not what is at just at the tailpipe. It is in a life cycle analysis that this is the only thing that counts, and we have said this many times yesterday. So we did a study, IFPEN did a study in 2022 with a brilliant team of life cycle analysis people. And the red car is the fully electric car, 60 kilowatt-hour battery. The blue one is a plug-in hybrid running 60% of the time on ICE mode and 40% in electric mode. And in 2022, with today E85, so with 25% of fossil gasoline, at European level with the electricity mix of Europe, we see that the blue car is 25% below, the plug-in hybrid is 25% below the electric car today already in 2020. And in 2040, with big assumptions for the decarbonization of the electricity mix at European level, the fact that batteries will be built in Europe, etc., the plug-in hybrid is still below, and it will run with a fully renewable E85. So that was for Europe, with obviously electricity mix that is with more carbon than the French mix. But even with the French mix, which is nuclear, and thanks to nuclear, it's very low in CO2 emission. In 2022, it was at the same level, the blue car and the red car, 13-ton CO2 equivalent for 150,000 kilometers. And with the same assumptions than the previous slide, in 2040, with a fully renewable E85 and 40% electric, 60% ICE mode, it can be below the equivalent electric car. So this was for the climate part. Now it's for the air quality, the pollutants. So in 2024, a new study was done on a roller bench testing 3 types of renewable gasoline. So bio-naphtha, which is a co-product of HVO diesel and HVO SAF. E-naphtha, which is a co-product of e-SAF. And ethanol to gasoline that is used today in motorsport. So basically, the car used was a Ford Focus, mild hybrid, flex fuel. WLTP test was done at 23 degrees Celsius, and these 3 types of fully renewable E85 were tested. And we measured the 4 main pollutants, HC, CO, NOx, and PM10, like that is asked for in Euro 7. And every single pollutant is very low compared to obviously to the Euro 7 limits, and especially with the bio-naphtha and e-naphtha, with the PM10 emissions. And even compared to E10, which is the main fuel today, with 10% ethanol, 90% of gasoline, the bio-naphtha especially is very low for all the pollutants, and again, especially with the particulates. The reason for that is just chemical, because we replace gasoline that has some aromatics that are precursors for particulates, and we replace with e-naphtha or bio-naphtha that doesn't contain any aromatics. So it's logical, but it's good to repeat it. Another point, because maybe when you know bio-naphtha and e-naphtha, you know that the octane is very, very low. And how can it work in a car that is flex fuel, a normal car? The good news is that when you put 50% or more ethanol, the octane is not just linear with the addition of bioethanol, it's exponential. So it increased very fast at the beginning, and then there is a plateau. And that's why, thanks to this chemistry, we can just replace today gasoline with the bio-naphtha in naphtha, and have a fuel that works in the fuel, in the car, I mean. Just to know where does the bio-naphtha and the e-naphtha come from. So it's a great chart from Fuels Europe, figures from Fuels Europe, and we did the chart ourselves. So for the HVO side, we have to know that when a SAF plant is producing SAF, or eSAF plant is producing eSAF, we never have 100% of the SAF or eSAF. We always have co-products. So smaller molecules that are naphtha, and they have to go with the gasoline pool together with ethanol to boost the octane, and the bigger molecules that are HVO diesel or e-diesel that need to be valorized in trucks, in diesel trucks engine. And to reply to some politicians that usually say that all biofuels should go to aviation, to decarbonize better aviation, you need to valorize all the co-products, the smaller one in the gasoline engine and the bigger one in a diesel engine, to decrease the price of the SAF and to go faster on the decarbonization of aviation. Just about the availability and basically how many cubic meters of ethanol can make how many plug-in hybrids on E85 fully renewable in Europe. So today we have 9 million cubic meters of bioethanol capacity in the whole Europe. If we consider that this represents the 75% content of ethanol in E85, you need 25%, so which is equivalent of 3 million cubic meters of renewable gasoline. These 12 million cubic meters of fully renewable E85, they can run 26 million plug-in hybrid flex fuel car running with a 3.5 liter per 100 kilometers. And this is 10% of the European passenger car fleet. So the politicians should not be afraid that we are not close to 100%. In the battery electric vehicle, we have plenty of space. But at the same time, it's not 0.1%. So it is not nothing. It is a solution to decarbonize all the use that will not be decarbonized by electric cars. And also that it already exists, this E85 fully renewable in California. They already blend bioethanol and bio-naphtha since 3 years at least. So the last few years, it was 1/3 of their volumes. And out there, they don't even promote it or make any publicity advertising on that one. They just use bio-naphtha when it's cheaper than fossil gasoline, and fossil gasoline when it's cheaper. So yeah, it means that it is used today in 1 million or maybe a little bit more than 1 million flex fuel car in California. So it's doable. And in Europe, we need to adapt the logistic and adapt the 85 standard, but we are already working with that and with some refiners, producer of HVO that have bio-naphtha or producer of eSAF that will have e-naphtha to take care of that. Any questions?
Thank you, Nicolas. Some questions to Nicolas? No question. Everything is clear for you? Yeah. Okay. So thank you very much, Nicolas. Yeah. Thank you. Anyway, it was a very great presentation. Thank you very much, Nicolas. So. Donc je vous propose de continuer maintenant sur la partie analyse de cycle de vie en accueillant Maxime Lucas. Donc Maxime Lucas qui est ingénieur chercheur en analyse de cycle de vie et co-conception à IFPEN Énergie Nouvelle. Donc, Nicolas va nous présenter des analyses de cycle de vie pour le transport maritime, méthanol, donc bio-méthanol et ammoniac, gris, bleu, ammoniac. Donc voilà. Maxime, the floor is yours.
Bonjour à tous. Merci Florence pour l'introduction. Hello everyone, good morning. I'm very happy to be here today to share with you some insights about the decarbonization potential of methanol and ammonia for maritime transportation. So you've probably heard that earlier this month, the International Maritime Organization, IMO, just approved a historic framework to reach net zero for the global shipping in 2050. So why is it historic? Because it's the first in the world legally binding framework that combines increasing requirements on GHG fuel intensity with starting with multiple compliant technologies at first. So there will be LNG, blue fuels, onboard carbon capture, and conventional biofuels that will meet these requirements. And after 2040, only some limited options like near zero GHG fuels such as e-fuels or advanced biofuels will meet these requirements. So this will combine these GHG increasing limits with pricing and reward mechanism. So it's a carbon market, GHG market, specific to the industry sector. And this will create, this is expected to create certainty, increase investment, and ensure e-fuels are cost competitive during the adoption phase, so before 2040. So there is a strong regulatory push for e-fuels adoption to decarbonize the maritime transportation today. So we've seen a lot of new e-fuels projects that are blooming around the world. So here are the e-methanol and e-ammonia e-fuels projects around the world. So today there are more e-ammonia projects because they are mostly for fertilizers production and also hydrogen transportation. We see it's the dark gray bubbles. Most of the e-ammonia projects are located in regions where there is relatively low cost of green hydrogen because of the high renewable potential. So a lot of them are in Chile, Egypt, Australia, or India. And e-methanol projects, they are more focused in Central Europe or in China because it requires to mobilize carbon capture. And China, so these are 2024 data, but China just announced numerous new large-scale projects that reached final investment decision stage, and they aim to become world's leader producer of e-methanol. The e-methanol is expected to be geared towards the chemical industry, but also the maritime transportation. So we of course expect more of these projects in the coming years because of this strong regulatory push, but also because the technology bricks are today mature. Haber-Bosch for ammonia is a well-known process, just like the methanolation process. So CMA CGM, a major transportation company, commissioned IFPEN for an independent study on the decarbonization potential of these two molecules. They could be derived from green hydrogen, so that's what we call e-methanol or e-ammonia, but also biomass-based, so biomethanol based on waste residue or farmed wood, and ammonia from blue hydrogen. So we've looked at the impact at different time scales. So what if the fuels was produced today or in 10 years or in 2050 in various location production. So in 17 production regions that we've considered, with or without the impact of transporting the finished fuel to a bunkering site, so either Rotterdam or Singapore. We've also assessed different energetical configuration and with or without taking into account the infrastructures. But to truly understand the decarbonization potential, we had to go beyond the GHG comparison on the fuels level, so per energy content. We've also computed the comparison at transportation work level, meaning what would be the impact of ammonia and methanol transportation of container. So basically we switched the functional unit to compare from grams of CO2 per megajoule to grams of CO2 per container transported over a certain distance. So that led to the main outcomes of this study were the energy flow analysis of all the configurations studied, GHG comparison between the regions and between the scenarios on bar graphs or in visual maps, cartographic maps, and all of that is available since last month in a public report. So before digging into the results, a few words about the methanol. So for methanol, we need CO2 gas and hydrogen. The CO2 gas, we can either capture it on concentrated flue gas. So we've assessed the option that it was powered by natural gas, but also electrically powered. And we've also assessed in 2050 direct air capture for the CO2. For the hydrogen, we've modeled the green hydrogen, so using renewable electricity for water electrolysis, accounting or not for the infrastructure of the renewable photovoltaic panel or wind turbines, because the RED regulation says that we should not account for this infrastructure, so account for 0 grams of CO2 per kilowatts of renewable electricity produced. We've also assessed the gray hydrogen pathways, so through natural gas steam methane reforming or autothermal reforming. Autothermal reforming is a much more advanced technology, yet it's still at TRL5, so that will only be for our scenario in 2050. And we've also assessed the blue hydrogen pathway, which is including carbon capture and storage on these SMR or ATR bricks. So of course, we've modeled all the downstream value chain of the methanol once it's synthesized for the conditioning, but also the transport to the bunkering site. We've assumed that the transport today was made with fossil fuel sea tankers to transport the ammonia or methanol. And in 2050, we assume that the transportation of the fuel was made with the own methanol or ammonia it transports. So it's a self-fueled vessel transportation. So all along this value chain, we need some energy inputs, and we've tried to assess comprehensively all the potential options, what kind of energy is used where, so we have a better overview of the real impacts of the e-fuels. So here you're looking at the results, so it's a probabilistic distribution of the well-to-wake GHG intensity of the different methanol configurations studied. So on the x-axis, you see the GHG intensity, and you see the red dotted line is the RFNBO thresholds, so 70 GHG reduction compared to the fossil reference. And everything that is on the left side of this red dotted line can qualify as RFNBO. So you see the e-methanol, depending on the configuration studied, is around 20 grams of CO2 per megajoule, and the biomethanol from waste wood is around 10 grams of CO2 per megajoule. We've done the same for ammonia. Ammonia, we don't need carbon capture, but we need nitrous gas to be combined in the Haber-Bosch. And if this with hydrogen, and if the hydrogen comes from blue hydrogen, then we have blue ammonia, and we have impact around 75 grams of CO2 per megajoule. So it's 20% less than the fossil reference. And if we are looking at the e-ammonia, this is similar results than e-methanol. It's around 18 grams of CO2 per megajoule. But once we have assessed the GHG results at fuel level, we need to understand what would be the impact at container transportation trip level. So for that, we've compared with the conventional trip that is fueled with VLSFO, so fossil oil, that emits around 30 grams of CO2 per container transported over a kilometer. And we've compared this trip if the VLSFO was replaced with ammonia or methanol, so to fulfill the same amount of work than the fossil trip. So we see this transportation trip with these alternative fuels will depend on two things, the GHG intensity of the methanol or ammonia, but also the energy consumption of the ship. So for that, we've used CMS-EGM computed data for engine conversion efficiency of methanol and ammonia boats and pilot fuel consumption. So what we see is that ammonia, for a given x-axis, the ammonia transportation trip emits more GHG emissions than the methanol transportation trip. This is due to lower ammonia engine efficiencies, because it's yet in research and development stage. But also, so that's why the curve is steeper for ammonia than for methanol. But also because we need more fossil fuel for the pilot fuel consumption to ignite the combustion in ammonia engine. So that's why the ammonia curve starts higher than the methanol. So let us put the three plots together, and we can translate the GHG emissions of each fuels into the impact of the transportation of each fuels, of the container. So we have the blue ammonia. The blue ammonia enables 20% GHG reduction threshold, GHG reduction compared to fossil reference. But if we look at the transportation work using e-ammonia, blue ammonia, we see that it is worse than the conventional trip. So in the end, using blue ammonia for a transportation trip is not reducing the GHG intensity of the transportation work. We are doing the same for e-ammonia, and we see that it enables to reduce by half the GHG emissions compared to the conventional trip. And for e-methanol, even though it's slightly more GHG intensive than e-ammonia at fuels level, because of the conversion efficiency that is greater for methanol, it enables to reduce more the impact at transportation trip level. And biomethanol enables to reduce by 80% the impact. So that was some conclusion we've drawn from current technologies, state-of-the-art technologies, that we've modeled through foreground data. So that's our inventory, our assumptions that we've used. For example, the electrolyzer conversion efficiency that we've modeled with our background data, which is EcoInvent, which is supposed to reflect the environmental impact of the global economy today. But if we want to assess prospectively the impacts of the fuel in 2035 or 2050, we have to make technological evolution assumptions based on experts saying, literature, or even regulations, to say that the electrolyzer efficiency in 10 years will be this much, or that will use, for example, direct air capture in 2050. So this is our foreground assumptions. But we also projected the background data, so our EcoInvent database, to reflect better the potential impact of the global economy in the future. So for that, we are coupling our today's EcoInvent database with integrated assessment models that reflects the global economy impacts following different scenarios. So the scenarios that we've chosen are middle of the road, and climate policy are national determined contributions. So this is the global economy decarbonation assumptions. So this enables us to compute prospective results for blue ammonia here and gray ammonia. So we see that the impacts are expected to decrease over time in 2035 and 2050. And on the x-axis, you see all the production regions that we've assessed. So the impacts are expected to decrease, so that in 2050, the blue ammonia using optimized ATR with carbon capture is not reaching the 70% GHG reduction threshold in all the regions assessed. This is because we are still using natural gas, and natural gas supply chain has a high impact for supply chain extracting and transporting the natural gas. So even with optimized assumption, optimistic assumptions, the blue ammonia in 2050 does not reach every time the 70% reduction threshold. Another conclusion we can see is that the transportation and conditioning of the fuel to Rotterdam, so this is the purple contributor, is a significant contributor, highlighting the need to transport the fuel, to produce the fuel close to the bunkering sites. And in 2050, if we auto-consume the transported fuel for its own transportation, then we can reduce this impact further. So to wrap up, we've seen that the e-fuels, following the Renewable Energy Directive methodology, enables to save the GHG emissions by 90% compared to the fossil reference. But it does not account for the cradle-to-grave emission scope, so it leads to over-optimistic reduction emission potential. And if we assess the full cradle-to-grave scope, we've seen that it enables to reduce by 80% the GHG potential, the GHG reduction. So it still passes the RFNBO threshold. So looking at the GHG intensity of the fuels assessed, we've seen that e-methanol and ammonia, e-ammonia, have the same order of magnitude of GHG intensity. However, due to lower ammonia engine efficiency, we have higher overall well-to-wake GHG results at emission transportation trip level than methanol. We've seen that blue ammonia was not fit for decarbonation, as it increased, on average, the GHG impacts of a transportation trip. We've seen that e-ammonia is fit for decarbonation, e-methanol is fit for decarbonation, but it can pose challenges to reproduce because it will require to mobilize carbon capture and potentially biogenic CO2 capture or atmospheric CO2 capture in the future. And biomethanol enables to reduce by 80% the GHG emission savings, providing that it is produced with waste, so appropriate biofeedstock, and that is largely available in quantity. So we want to conclude this study with further comparisons with the LNG, e-LNG, and bio-LNG in the future. And yes, thank you very much for your attention. I'll be happy to answer any questions.
Thank you, Maxime. Some questions?
Thank you very much for the presentation. Two questions. The first one, regarding the e-fuel GHG, are you working on a curve based on the intensity, carbon intensity of the electricity for various countries, as you did with the ammonia? That's, I would say, a question for future works, maybe. And the second one, and I agree with your conclusion regarding the e-methanol versus the e-ammonia. Ammonia, according to design as an engineer, is a failure of the first rule of safety inherently. If there is a leak of ammonia, you don't matter to try to cope with the leak. You're dead before you notice it. But so, according to you, why is there a kind of hype of e-ammonia when we see your result with e-methanol, which is much safer and inherently better in terms of GHG emission?
Well, thank you for the question. For me, it is because e-ammonia is easier to synthesize because it doesn't require CO2 capture. So that would be the main advantage I see. And it's always easier to transport, and the supply chain is easier than direct hydrogen. So it's, for me, the alternative between H2 and complex synthetic fuels. So that's why I think the transportation companies are interested into ammonia. But yeah, I cannot say much. Sorry.
Thank you, Maxime. An additional point, I think you focused on methanol and ammonia, which are the two largest commodities worldwide, which is important for a carrier like CMA. But an interesting point could be that the most available low-carbon molecule worldwide is ethanol. Did you do a comparison with bioethanol or advanced bioethanol?
Yes, we've done for CMA-CGM a comparison, but it was later on. The study was already almost finished when they got interested into bioethanol. and we don't have the engine conversion efficiency data right now to put everything on the same plot, but we can ask them to have this. And I think they realized that methanol could run into ethanol engine as well. So that's why they could use both methanol and ethanol. So yeah, there is also a strong interest in ethanol.
Thank you. And some other questions? No? So thank you very much, Maxime, for your presentation. Et ce que nous vous proposons maintenant, c'est de terminer ce panel de présentation avec Jean-Baptiste Jarin. Donc Jean-Baptiste est chercheur associé au laboratoire TRI de l'UPPA. Il a fait une thèse doctorale pluridisciplinaire, énergie, économie, sciences politiques et droit sur la décarbonation de la mobilité aérienne. Et donc Jean-Baptiste, pour terminer cette session de présentation, va aborder les enjeux de justice énergétique pour les e-fuels et l'hydrogène, qui sont bien sûr au cœur de la transition énergétique. Donc Jean-Baptiste, the floor is yours.
Merci. So I understand I have to switch into English as well. Okay. So I will try to do so. As an introduction, I was not there yesterday, so I apologize for that. But just a reminder, a few fundamentals. The first thing is that we do not create energy. We pick the energy in the environment and we convert it. So that's very important when we look at energy carriers and then at the scalability that we can have when using the inputs, and the inputs being biomass. There have been a lot of presentation on biomass this morning, and tomorrow perhaps electricity, either for hydrogen or ammonia, but you understood with my question that I'm not a big fan of ammonia, and e-fuels, which according to me is the least inefficient energy carrier we can have based from electricity for some, I would say, applications. So that's it with that. Yes. Also, to start, the main things for me, you understand that the technology is most of the time mature. It's still improving in terms of efficiency, but globally the technology exists. And so the big questions for our societies are for the inputs, the biomass and the electricity. When we have the inputs, we need to look at the energy carrier and the losses we have in the conversions. And I'm always, I'll phrase it that way in English, I try to be pragmatic with technological neutrality. I understand that yesterday we say technological neutrality everywhere. For me, it doesn't make sense if it doesn't come along with the final use and the carrier. If I pick the examples of cars and planes, because my PhD was on planes, on air mobility, for a car, there is no issue. Electric vehicles are far more efficient than anything else. For planes, it's the opposite. Direct electrification in a plane doesn't make sense at all. We need to run with a liquid fuel. And e-fuel and biofuels are a must, for example, for hard-to-abate sectors like planes. And even if I'm not a specialist, from the lectures I have, would be the case also for maritime. So when we understand that what we need are inputs, we need to look at the inputs. We had great presentation this morning. Some of the questions were about the economics and are the biomass producers willing to sell their products? I would add, is there any conflict of use for the products? Because most of these products are already used. We can look at the biomass in general, but I'll share with you one experience I had with HEFA, the sustainable aviation fuel we use for aviation. HEFA today is the most common SAF for planes because it's the cheapest one. And it's based mostly on tallows, but mostly on used cooking oil. The price of used cooking oil from 2019 to 2022 and also in 2024 today has been multiplied by 3. So the used cooking oil left a channel of 600 euros per ton to reach 2,000 euros per ton. And for some months, used cooking oil was more expensive than virgin oil, which led to some frauds, etc. So every time we have a look at an input, at a biomass, we need to understand what would be the collateral effects along with those. So we know how to produce. I think we celebrate very soon the 100 years for the Fischer-Tropsch, for example. So we know how to make synthetic fuels for 100 years. It is not very much used for a single reason. It's because it's costly. And so the countries which use synthetic fuels did it because of geopolitical reasons. That's the case of Germany during World War II. That was the case of South Africa during the apartheid today. And now we have a better reason to do it, which is the environment. So that is great, but we need to understand that it will come with effects and at least costs. So we need to make sure that the input is sustainable. We also need to understand the conflict of use, what is clearly the optionalities, and we need to understand the cost, which is mostly collectability. The studies we've done show, for example, that when you use first-generation biomass, for example, corn, that we've been discussing this morning, it economically makes sense as long as your collect point is within 50, 60 kilometers radius from your refineries. If you leave corn for dresch, which is stover in English, la tige, yeah. There is less energy in the dresch than in the corn itself. So the collectability goes from 60 kilometers to 160 kilometers. And at that point, you have no economical business case. And even in GHG, you have so many transportation that it doesn't make sense. So every time there is a study on the biomass and the inputs, and that would be the same for the electricity and the hydrogen, we need to understand what means in terms of collectability and optionalities. I just have one slide on, I would say, on the volumes available for the inputs. I think we are not that far from what has been presented this morning by Concawe. A little less optimistic, I would say. That is the slide here. Oh, sorry. That's a way back. That's the first slide. I would say it's like for the climate. What is the scientific consensus regarding the scientific studies? And what you have is that for each category of biomass, if it's red, is that there is no consensus. There has been a study, but there is no consensus. If it's blue, there is a high consensus. When we pick that, basically, we have an availability of 100 exajoules worldwide. So if I pick for Europe, I guess not that far, maybe a factor 1.5 on the two. So we have 100 exajoules of biomass available. Today, we burn 100 million barrels of oil equivalent per day. That means 220 exajoules, just that we understand the gap between what we use today and what we could get tomorrow. Moreover, that bioenergy is a bioenergy in general. It goes to, for example, for cooking in less advanced countries. It goes for heatings in some others. So the consensus regarding the availability of bioliquids is closer to 10 to 20 exajoules. So 10 times less than what we consume. And since my specialty is air mobility, I would say 10 to 20 exajoules. This is the volumes required by the air mobility in 2050 to try to reach the not carbon neutrality, but to try to reach the objective, which is to divide by 2 the CO2 emissions in 2050 compared to 2005. So this is my point here is to say that we need all those energies, but maritime and air mobility would most probably be the major outputs for all those type of biomass, and still it will not be enough, so we will need electricity. If I convert once again electricity, 100 million barrels of oil per day, if I convert that into electricity to produce those volumes, it's 120,000 terawatt hour. The world today produces 25,000 for all the usage. So that doesn't include that needs for the replacing oil with e-fuels, or it would be the same values for hydrogen, more or less. So the objective from the International Energy Agencies for 2050 is to reach 55,000 terawatt hour. So you can see that we fall short, and this doesn't take into account any major replacement of oil replaced by H2 or NH3 or e-fuels. So there will be tensions, like for the used cooking oil, I showed that example, there will be tensions on the biomass markets and also on the electricity markets. On the biomass market, this is not a study from me, that comes from the Academy of Science of United States. It's a one-year-old. What it shows is that in Europe, we now have a cap on first-generation biofuels. In the US, it is still supported. There has been the donut gate for those who are interested. This is a competition between the bakers, the donuts, the bakers, and the producers of biofuels in general. But what the study showed is that after 15 years of subsidies and supporting the biofuels for cars, the impact on the price of commodities of corn, soy, or wheat has been plus 20 to 30% for the price of the food for the people. So all our action always has an impact within our societies. And there, we expect that there is the same type also of imbalance between offer and demand for electricity as soon as there is a strong demand for H2 and or e-fuels. Would be the same for the price of electricity. If there is a higher demand than the offer in an unregulated market, the driver is a price. Here is a reminder and to say why we have chosen the type of fuels. I'm sorry if the graph is not very sexy there, but I'll try to explain it. And why the tensions will be more important on hydrogen and in fuels than it has been shown on the biofuels. This is the energy return on energy invested. When we talk of energy in general, it's not always appropriate. It's more appropriate for exergy, I would say. But as soon as we focus on liquid energy, it really makes sense. And what it says is that basically for the good old oil, so the conventional oil, the energy return on energy invested is between 20 and 70. So you bet one, you get 20, or you could get 70. If you go in the Middle East, it would be closer to 70. If you go to North America, closer to 20. Then we went to offshore, so you can see that it's declining. Ultra deep, then we have the titled, then we have the tar sands, then we have the first synthetic fuels, the coal to liquid and the gas to liquid. This is what Germany and South Africa used in the example I gave earlier. And then we have the biofuels. So generally, for the first generation, it's higher, 2 to 4. So this is why, generally, we still like them. It's because they have more, I would say, a better economic sense. In terms of environment, it could be discussed. And then we have the e-fuels. The e-fuels is 0.4 to 0.6, which is to say that every time I will pick 1 kilowatt hour on the grid, I will get a maximum of 0.6 and generally closer to 0.5 in my tank. And then it will go in my engines with an efficiency which can also be discussed. But let's say at the end of the road, at least for planes, I can be very direct for planes, the overall efficiency is 14%, 14% from the electricity we'll pick from the grid. So we need to be very cautious because we will need a lot of electricity. And then comes the type of fuels we have. If I try to illustrate for France and Nouvelle-Aquitaine, because it's the area we're here, so this is part of the work we've done 3 years ago, almost now, with the Académie des Technologies. This is, for me, the major graph of that report that was published 2 years ago. It takes France. France today, we use 60 million tons of oil product, 60. Of those 60 million tons, 7 are used for kerosene, for jet fuel. And so the report was on how France could produce part of the jet fuel we need. And so we first look at the biomass, and since it was not enough, due to conflict of views mostly with the biogas industry, which was the sense of my question to my colleague of Germany, on the way, we had a cap in terms of biomass availability to 6 million tons. Some could say it's low, some could say it's high, but it was a cap. And then we say, okay, still, it's not enough to produce the volumes required for France, so we will need electricity. And I would like to, and I think it was well done by Concawe, Europe is gifted And France is gifted. We have biomass and we have low carbon electricity compared to the world, to other regions in the world. If I pick low carbon electricity, France is in the top 5, EU is within the top 12, and in the top 5 you will find smaller areas like Quebec, like Northeast Brazil, like Iceland, which is very low in terms of volume. So really Europe and France are gifted. And so the goal for us was, okay, perhaps we don't reach full sovereignty, but at least we need to bring some exemplarity because we have the inputs. And so we try to produce at least half of the need. And so that's the green curve. We try to say, okay, if we want to produce 4 million tons by 2050, so half of the need for aviation, how many biomass we need and how many electricity. The result is a 6 million ton biomass, which was a cap for us for the availability in France, and 100 terawatt hour, knowing that France plans for 2050 is 500. So that's 20% of the electricity production of the country that we need to divert to feed aviation only. If you look at maritime, generally you multiply by 2. Okay, aviation and maritime are very close. We both use 7 to 8% of the fuel worldwide, the fuel production worldwide. So it's a good match, and I think it was on the presentation of ethanol. Generally, we appreciate that when we produce biofuels or e-fuels, we can have a 50-50 share between heavy for maritime and not lighter, a little lighter for the kerosene, for the jet fuel. If we go to Nouvelle-Aquitaine, we have a huge history in chemicals, thanks to the Bassin of Lac, which is nearby. And there is a project which I strongly support because I think it really makes sense. It is the most efficient, from what I studied, pathway for that, which is called ECO. ECO aims to produce some naphtha, mostly SAF, but also some naphtha and some co-products. But roughly, if we say virtually only producing SAF, it would be close to 0.15. So let's say between 0.1 and 0.2 million tons per year. Okay, we burn in France 7, 0.1 to 0.2. To produce those volumes, it needs 300 kilotons of forestry residues. This is 15% of the forest of Aquitaine, which is one of the largest of Europe, the second largest of Europe. So that's 15% of the forestry residues of the Nouvelle-Aquitaine, and it requires 4 terawatt-hours of electricity, and that's close to 8%, a little above 8% of the production of the Nouvelle-Aquitaine. So a single unit, which will produce a few percentage of the need of aviation only, by the way, requires 8 to 15% of the inputs of a single area. And so we need to make sure that when we do that, well, first it means that we cannot have 10 project equivalent all over France, most probably be close to 3 when we pick the right areas. The second is that we need to be very cautious regarding the impact it could have on our societies. So we focus on the electricity. We need electricity. I mentioned e-fuel. I support e-fuel, to be clear, but in a reasonable way, a reasonable manner. I think it's much more efficient than H2, at least for aviation, but for most kind of application. But H2 is a very precious molecule, and we need to be wise when we use it. Once again, just a reminder, to produce H2, we need, in a perfect world, 40 kilowatt-hour of electricity to split H2O in H2 and half O2. In an industrial world, it's closer to 50-55. That's before compression and or liquefaction. So 50 to 55, it's what we would reach in a very good industrial process. The lower heating value of H2 is 33 kilowatts. So this is the 0.4, 0.6 I mentioned before. We will need 50, 55, if we liquefy, maybe 60, 65 kilowatt-hour of electricity to get a molecule which has a lower heating value, so the work we will get from it of 33. Okay? Still, and I think, Florence, you made in the introduction, the hype on hydrogen is slowing down or going down, and I think that's a good thing. So we need hydrogen, but for people who believe in hydrogen in mobility, we could have some long discussion next to the fireplace for that. But in the world, that is a year ago, May 2024, this was a report of the International Energy Agency. It's not in the report. I picked the different projects and number which were in the reports. And we can see that there was the objective that by 2030, we would reach almost 100 million tons of hydrogen. Wonderful. Europe was in that hype. Initially, Europe said we want 20 million tons of hydrogen. And then it came to want to produce those 20 million tons in Europe. Then they say, okay, maybe we will import part of it, and now the full numbers is declining. But when we see a hype model, and then before seeing the consequences for the populations, what was already interesting to notice, it is that you have a lot of projects, but I would say the more far you are from the operational and even from the fundings, I would say, from the final investment decision, which is the second one, the size of the project gets bigger and bigger and bigger. And some projects where, I will pick Mauritania as an example because it's close to us, and the EU made a partnership with Mauritania. For some project, it was above 1 million tons. Okay. The reality today, and at least for the population, here I try to summarize what it means. So the soufflet of hydrogen is going down, and that's a good thing. But here I put France so that we have a benchmark. But most of the projects for hydrogens are in the global south. And we say, oh, it's easy. They have sun, they have wind, they have space, and maybe we will import from those places. If I pick Mauritania, Mauritania is currently producing less than 2 terawatt-hour of electricity. Still, the project listed by the International Energy Agency says there is almost 5 million tons of production by 2030. So in 5 years' time, producing 5 million tons of hydrogen would require 316 terawatt-hour of electricity. So before you put your money and you invest, you need to have a look. The country only produces 2, but we have projects that would require 316 terawatt-hour of electricity. This is almost the nuclear output of France, okay, to give you a scale on there. And then there are effects at least I would say this has effects on investors. Why not? It's not my money, it's okay. But it can have effects on populations. So if we pick the population, for example, half of the Mauritanians do not have access to electricity. They have no electricity at all. So is the EU willing to sponsor, I would say, the production of wind and or solar, which for me is not the panacea for hydrogen production, because hydrogen production requires stable, I would say, electricity inputs, which is not the case with wind and solar, but that's something else. And tell the population this is to provide European cars and planes with e-fuels, but we don't care if you don't have access to electricity. For the others who have access to electricity, the average consumption per year is 400 kilowatt-hour. This is 20 times less than what we enjoy in France. Then we have a network, a grid, which is very inefficient with significant losses. And last but not least, the production of electricity is heavily fossilized, to use the word of Florence this morning. So should the priority be A, access to electricity to the population, B, decarbonizing, defossilizing the electricity production of the country before exporting an inefficient, but necessary, but still an inefficient molecules elsewhere in the world. So that the first point regarding energy justice, and the idea there is that at least within the EU, along with the delegated acts, which according to me are very clever, especially temporality and proximity, are very, very clever, should we add, when we decide to import, other criteria such as those, so that we avoid exporting energy injustice abroad. And finally, it also works for us in Europe, and here I pick France, and I'm very sorry because I think it's not quite visible. but I will share the slides. And this is part of a publication which was published 2 months ago in Climate Policy, so you can find it. You can find those graphs. What it says here is that for own economies and societies, massive productions of electricity-based energy carriers could have an impact. I told you my specialty is air mobility, so I picked the e-fuel for aviation. Producing hydrogen and therefore e-fuels, or producing e-fuels and therefore hydrogen, because we need a lot of H2, by the way, is definitely electro-intensive. No problem for that. So we have a regulation which makes sense, and we want to keep those electro-intensive industries in France or in Europe, and that's perfect. We need to do that. The problem is that when we look at the gap of the different taxation rates and subsidies for the production, and we compare for the other part of the population and the other part of the industries. For the industries, this is the electricity we pay as a household. Sorry. So this is electricity we pay for households. This is the electricity that industry pays. It makes sense. They buy in bulk, so no problem. This is the price of electricity for electro-intensive. Okay. If the electro-intensive is for producing a final product which is then taxed, why not? At the end of the day, there is money coming back. And why not? If it goes into a product which is untaxed, and which is the case for the e-fuel, typically for aviation, then there is an issue. There is an issue because basically it means that tomorrow flying, if I pick the Maldives or whatsoever, abroad using e-fuel or to power the plane, it means that traveling abroad, which is a tertiary need for sure, is 3 times less expensive than the electricity we all pay for basic needs like heating, cooking, cooling, and whatsoever. Electricity in our modern economies is an essential need. We've seen it in Spain, I think yesterday. We need electricity. We cannot live without electricity for, let's say, a day or two. Then we have a big issue. So this is the point that we need to make sure that within our taxation rates and in terms of incomes and redistribution, we do not make a market that would provide, I would say, societal instability. And the last example would be for the road transportation. If we pick e-fuel for road transportation, and for me, clearly, it's a nonsense. If we pick the same price of electricity, let's say, to feed your cars or to feed the cars with direct electrification or with an e-fuel, it's already an issue in terms of taxation. Because for sure, there is less money coming to the government when you plug your cars. Even at 25 cents, electricity is heavily taxed. It's as taxed, even more taxed than fuel today. But since we need lower consumption, far lower consumption, because we are five times more efficient, the gap I would say, is less important than when you use an e-fuel. If you use an e-fuel, and we've seen some price for the biofuels before taxation, the price for an e-fuel using an electricity at 25 cents, so it's the same price than feeding your electric cars. It means it's not €5 for 100 kilometers, it's €35 for 100 kilometers. So then the point would be which country can afford, I would say, such a gap, and if it does, will it leave the population to bear the cost, or will it bring lower taxation or even subsidies to narrow the cost, the price difference? And this is it.
Thank you, Jean-Baptiste. Thank you, Jean-Baptiste. We will take a very short question. John?
Yeah. Thank you, Professor Sharon. Is that? Yeah. John Cooper. I was at Fuels Europe and Concawe for a few years. I'd just like to test you on a couple of your biases there. You're focusing very much on efficiency, right? I guess I would point out that there are different types of efficiency, and you're talking clearly about a technical energy efficiency there. There's also something about the efficiency of storage and transport, and I guess I'd make the observation that if I look outside just about 95% of what transport works today globally is working on a liquid fuel. And also in the natural world, just about everything that moves uses alcohol, fats and sugars for moving. You'll see songbirds that will go from one continent to another on a few grams of fat. And electricity storage basically doesn't exist in nature, and it's pretty hard to establish today. Some of the studies that we've seen this morning indicate far higher biomass availability within Europe than the figures that you've been describing. I guess I would make the observation that maybe we should be making a huge effort on getting better at managing energy molecules, and that while we have to do electrification, you have to do more effort on molecules as well. I'm not sure you're quite there in your studies yet. Can you make a reaction or an observation based on just what I've said? Thanks.
Yes, of course. I would say energy carriers do not exist in nature as well. We are living primary energies for energy carriers. So we will manufacture those energy carriers. As soon as we manufacture an energy carriers, we need to be efficient. And yes, we disagree, I would say. So either we build plants and storage for e-fuels, and I think we agree for planes, there is no issue. It's a far more efficient way to transform electricity for planes, because carrying batteries doesn't make sense at all. But for a system like a car, all scientific studies goes that there is an efficiency between 84 and 91% for electric cars when we use electricity from the grids, and we will go, if it goes into an internal combustion engine with an e-fuels, which is the objective of the e-fuel, would be closer to 14, 16%. Which country, which area of the world can afford to, I would say, to lose 3-4 times the efficiency from something we will manufacture? It's not in the nature. We will manufacture in both scenarios.
But the point is there are many technologies to get to those molecules, right? And you're picking the one that's the least efficient to put on the flagship of your argument.
No, the e-fuel is the e-fuel. It can be manufactured from different processes, but at the end of the day, it goes, you pick the Sankey chart. At the end of the day, you would be close to 15%, let's say plus or minus 20%. Okay. That's the point. And since you go in that direction, because I have the chance to discuss very often with one of your representatives at the Renewable and Low Carbon Fuel Alliance at Brussels. By the way, I would be very, and I express my opinion here, disappointed that the EU withdrew from the 2035 ICE ban for several reasons, but for one that I never hear in such comments. This is the most efficient, I think, I hope you would agree with that at least. But on the second is that if we, before the PhD, I've done my master at Mines ParisTech. So we have a strong focus on minerals, I will say in Mines ParisTech. Minerals are for sure an issue. But if the EU is not at the forefront of the electrification with batteries, we will lose all the wars for the coming decades. Why I say that? Batteries can be recycled. There will be tensions on the minerals, and I think we agree on that for sure. If we don't have those minerals in our territories, I would prefer they are manufactured in the EU and so on, but what's most important is that within 20 years, we have those batteries, those minerals, the mines of the future in our territories, because for sure, the fossils at some stage will go down. And so we need to make sure that perhaps after China, but at least before North America, we have those mines in our soil so that we have some sovereignty.
Okay, so we see that there are some discussions and some different positions. So let me just short the exchanges now because it is a break. I think that we will come back after the break with the scientific committee to draw some lessons on these sessions, and we will again discuss the important point of technology neutrality.
Merci beaucoup. Merci Florence DELPRAT-JANNAUD. Petite pause, 5 minutes, café, jus de fruits, viennoiserie. Merci à l'ensemble des présentations qui ont été faites ce matin. Thank you very much. Just a break now with coffee, orange juice and viennoiserie you want on the terrace. Thank you. Je vais vous inviter à prendre place afin que l'on puisse maintenant donc effectuer cette table ronde de synthèse en présence des différents membres du comité scientifique. J'essaye. Voilà, nous allons reprendre maintenant donc pour la synthèse, également pour les différentes analyses suite à ces présentations. Florence DELPRAT-JANNAUD, je vous laisse bien sûr diriger toute cette partie synthèse et conclusion également après ces différentes présentations. Merci.
Si, Maria,
alors nous avons une intervenante, Maria Georgiadou, donc en visio qui va être en permanence sur l'écran derrière nous pour terminer cette partie-là avant la conclusion avec Valérie Demangel dans maintenant une petite trentaine de minutes. Merci.
Anne nous rejoint tout de suite. Excusez-nous, j'envoie un mail à Maria. Merci beaucoup. Donc, je voudrais commencer par remercier les intervenants de ce matin. Donc, Abinash Ramasary, Nico Weimer, Nicolas Kurtsoglou, Maxime Lucas et Jean-Baptiste Jarin. Donc, merci d'avoir partagé vos travaux, merci d'avoir partagé votre vision technologique et scientifique sur un certain nombre d'enjeux, les enjeux de disponibilité de la biomasse, les enjeux d'analyse de cycle de vie, les enjeux en termes d'économie. Donc, on a vu aussi que sur certains sujets, il y avait des divergences. On a parlé des questionnements qu'on avait sur l'hydrogène. On voit que la place aussi de l'électrique pour la décarbonation du transport routier est aussi discutée. C'est normal. Moi, ce que je retiens de cette journée, donc j'ai envie de rebondir sur cette notion de neutralité technologique qui me tient énormément à cœur, et puis ça a été encore dit et redit. Donc bien entendu, quand on dit neutralité technologique, il ne s'agit pas de faire n'importe quoi, il s'agit d'utiliser les technologies là où on en a besoin et quand on en a besoin. On a vu donc qu'on avait à notre disposition un panel de solutions. On a vu aussi ce matin qu'on avait des ressources qui sont disponibles pour réussir cette transition. On a vu aussi qu'il fallait se poser les questions en termes d'économie, de compétitivité. C'est essentiel pour la décarbonation, c'est essentiel pour la défossilisation. Je reviens sur ce terme qui me semble aussi important. Merci d'avoir partagé ces nouvelles données. On a vu aussi des applications sur le maritime qui sont aussi très, très encourageantes. Et donc, ce que je vous propose aujourd'hui, pour tirer les grands messages de cette matinée, c'est d'accueillir sur scène les membres du comité scientifique, donc Raphaël Bourroman, Anne Bouter, Maria Georgiou devrait nous rejoindre par visio. Donc, et puis, malheureusement, David Chiaramonti ne peut pas être là parmi nous aujourd'hui. Donc, ce que je vous propose, c'est déjà de faire un tour de table sur les grands messages. Donc, je vais commencer par vous, Anne. Anne, vous êtes chargée de mission scientifique au JRC de la Commission européenne, spécialiste en analyse de cycle de vie. Vos travaux portent sur l'application des analyses de cycle de vie à toutes les filières énergétiques existantes, avec évidemment une attention particulière au secteur des transports. Vous avez une formation aussi solide en sciences agricoles et en agronomie, et vous menez des recherches sur les énergies renouvelables et les transports. Vos projets récents se sont concentrés sur la bioénergie et les carburants alternatifs, en mettant l'accent sur leur mise en œuvre dans les secteurs routiers et aériens. Vous avez publié beaucoup de travaux en utilisant les ACV pour fournir des outils d'aide à la décision. Et j'ai envie de vous demander, Anne, tout simplement, qu'est-ce que vous avez retenu des présentations de ce matin ?
Merci beaucoup, Florence, pour l'introduction. Bonjour à tous, merci à tous les présentateurs donc pour la session technique de ce matin également. Donc, on a vu différentes présentations qui ont bien donné un bon panorama de la nécessité d'aujourd'hui par rapport à la décarbonation de notre mobilité. Moi, ce que je retiens, c'est que, à mon sens, toutes les présentations vont dans le même sens, c'est-à-dire qu'il y a un besoin de décarboner notre mobilité, il y a un besoin de décarboner notre économie et donc de s'inscrire dans un contexte énergétique plus durable et de pouvoir également dans ce sens-là, atteindre les différents objectifs climatiques donc on peut se fixer en Europe, mais également potentiellement dans d'autres cadres de travail internationaux. Donc moi j'ai retenu quelques aspects clés des différentes présentations. Donc il a été présenté que, donc, et également hier, la mobilité contribue donc pour une part importante aux émissions de gaz à effet de serre. Et de ce fait, c'est un secteur intéressant comme levier potentiel de la décarbonation. Et donc pour ce faire, on a de nombreuses législations, réglementations, scénarios, je dirais, donc au niveau européen et internationaux. Donc ça nous a été présenté ce matin à travers différentes présentations. On a vu aussi que en ce qui concerne l'électrification, donc on a évidemment un gros potentiel sur l'électrification, mais on peut se heurter à certaines limitations. Donc pour certains secteurs qui potentiellement peuvent être plus difficiles à décarboner, comme les poids lourds par exemple, le secteur aérien, on en a parlé, le maritime également. donc à la fois liées à des caractéristiques techniques comme des densités énergétiques élevées ou des longues distances de transport. Et donc dans ce cas-là, c'est vrai qu'on a vu que la recherche et le déploiement de fuels alternatifs bas carbone prennent tout leur sens dans ces cas-là. Évidemment, les biocarburants et les e-fuels vont faire partie intégrante de notre transition énergétique. Ça a été également mentionné hier, mais la solution pour décarboner le secteur des transports et décarboner notre industrie et notre économie en général, elle ne va pas être unique. On ne va pas avoir une seule solution, mais on va en avoir plusieurs qui vont s'adapter aux différentes nécessités des différents secteurs et potentiellement aussi à un niveau régional. On peut envisager d'avoir aussi un maillage à la fois technologique et à la fois géographique. Donc encore une fois, merci à tous les présentateurs de ce matin et aux questions qui ont été posées, parce que je pense que ça donne pas mal d'idées pour la suite, pour de potentielles discussions et projets. Merci.
Merci Anne. Une petite question quand même, Anne, pour aller un tout petit peu plus loin sur la partie carburant durable. Donc les biocarburants, les électrocarburants, les biocarburants avancés, est-ce que vous voyez des priorités pour leur déploiement entre les différents secteurs, le routier, le maritime, l'aérien? Est-ce que vous avez des recommandations?
Alors, au niveau... alors, c'est pas priorité, c'est peut-être pas forcément... il ne faut pas avoir ce mot au sens de priorité technologique, mais peut-être plutôt au niveau de priorité temporelle par rapport au développement des différents secteurs. Donc, c'est vrai, on en a aussi un peu parlé. Au niveau d'un horizon temporel un peu plus court, donc sur le secteur du transport routier, je pense qu'on a déjà pas mal d'outils pour décarboner, donc notamment la directive énergie renouvelable qui va être mise à jour, des nouvelles valeurs pour les annexes 5 et 6 devraient être également proposées prochainement. Tout ça s'inscrit donc dans le cadre du package Fit for 55 de la Commission européenne. Ça a été également mentionné hier. Il y a un autre point plus infrastructure routière également, donc, qui a été également mentionné par le collègue du Parlement européen, donc, sur Alternative Fuels Infrastructure Regulation, donc, qui demande aux différents États membres de mettre en place un maillage donc, pour les différentes infrastructures pour le transport, donc bornes de recharge, stations hydrogène, etc. Ensuite, au niveau priorité moyen terme, donc là, c'est vrai qu'on identifie plus le secteur maritime. Donc, ça a été évoqué ce matin aussi avec donc, à la fois au niveau international, donc toutes les discussions qui sont en train d'avoir lieu dans le cadre de l'IMO, donc l'Organisation internationale pour le transport maritime, et également au niveau européen, donc en tant que stratégie européenne sur le maritime, et à plus long terme, donc ça a été aussi évoqué sur le secteur aérien, où là aussi on a un cadre au niveau européen avec ReFuelEU Aviation, et également un cadre au niveau international avec toutes les discussions qu'on peut avoir au niveau de l'ICAO et de Corsia.
Merci beaucoup Anne. Je me tourne vers vous maintenant, Raphaël. Raphaël Borouman, donc vous êtes professeur d'économie, conférencier, spécialiste des politiques énergie-climat. Raphaël, quels sont les messages de ce matin sur lesquels vous voulez rebondir?
Moi, je voulais un petit peu... Alors, bonjour à tous. Bonjour à tous. Merci à Valérie pour son invitation et bravo aux speakers ce matin pour leur présentation. Moi, je voulais élargir un petit peu le concept de décarbonation un peu au-delà du secteur des transports, qui est certes essentiel, mais plus largement à l'économie. Il n'y a pas finalement beaucoup de forums comme celui-ci où on fait le lien, on essaie de faire l'articulation entre décarbonation d'un côté, souveraineté industrielle, compétitivité de l'économie et sécurité d'approvisionnement. Il faut garder le cap de la décarbonation, il est essentiel, mais le but, ce n'est pas de faire, alors si on parle de l'Europe, une sorte de désert industriel ou une sorte d'îlot décarboné où finalement il y aurait très peu de CO2, mais l'Europe serait une sorte de débouché commercial pour la Chine ou les États-Unis. Et l'idée, c'est qu'on est face à un choc des titans, avec deux blocs offensifs, États-Unis d'un côté et Chine de l'autre, et que l'Europe a quand même des atouts. Et il ne faut pas perdre le fait que la notion de souveraineté, ce n'est pas un terme grossier, et que c'est un peu la fin d'une forme de mondialisation heureuse, et qu'on est à l'heure de vérité d'une Europe de l'industrie, et que la souveraineté, elle est certes sur les ressources, on en a parlé ce matin, et on en a parlé hier, mais elle est aussi sur les technologies, la souveraineté technologique. Et ça ne suffit pas de lancer quelques gigafactories en France, de fabriquer quelques batteries et de pompes à chaleur quand on importe l'essentiel du reste. Il faut mettre en place une vraie stratégie. La Chine a mis en place depuis 3 décennies une filière de terres rares et de minerais. Ce n'est pas pour rien qu'elle en est là aujourd'hui. Donc il y a un défaut d'anticipation de manière générale en France et en Europe qui consiste à penser qu'on peut changer de cap souvent. Alors si je prends l'exemple du nucléaire en France, je ne sais pas si vous vous souvenez, en 2017, on devait fermer 14 réacteurs. Maintenant, on doit construire 14 EPR. Bon, ça fait un petit delta de 28 réacteurs. Bon, en 8 ans, on pourra avoir un cap un peu plus clair. Alors, ce n'est pas une critique, hein, je comprends qu'il y a des alternances politiques, je comprends tout ça. C'est que s'il n'y a pas de visibilité et d'état stratège, ça va être un peu compliqué. Alors que d'autres pays se posent moins de questions. Alors, je vous donne l'exemple des droits de douane, parce qu'on en parle beaucoup. Alors, c'est intéressant de voir ce que vous en pensez, mais je ne suis pas sûr qu'il faille prendre des décisions d'investissement, notamment de fabrication d'usines, en fonction de droits de douane que le président Trump peut changer tous les jours, toutes les heures, toutes les semaines. On ouvre une usine pour 10, 15 ou 20 ans. Vous le savez mieux que moi, il y a eu des patrons d'entreprise qui sont venus ici aujourd'hui et hier. Il faut le faire sans tenir compte des droits de douane, j'ai presque envie de vous dire, parce que les droits de douane, ils vont changer en 20 ans plusieurs fois. Et qu'il faut cette forme d'autonomie stratégique, qui est un levier de la souveraineté, face à des pays qui s'organisent, par exemple, pour les minerais, comme l'Australie et la Chine. Car l'Australie vient de créer une réserve stratégique de 31 minerais. C'est utilisé comme une arme diplomatique, une arme économique. Et l'Europe, pendant ce temps, alors qu'elle pourrait développer, par exemple, une filière du recyclage, de la transformation des minerais, est toujours un petit peu hésitante, malgré des très bonnes initiatives. Il y a eu une législation, je crois, sur les minerais récemment, pour dire qu'il fallait qu'une partie soit extraite, transformée en Europe, qu'il ne fallait pas dépendre à plus de 65% d'un seul pays en matière d'importation. Bon, 65%, ça reste quand même élevé. Mais bon, il y a des initiatives aussi sur les batteries. Donc il y a beaucoup de choses qui se passent, mais je pense qu'il faut passer à une vitesse supérieure, là, parce qu'on est vraiment face à deux empires qui ne vont pas nous faire de cadeaux en tant qu'Européens. Je continue ou je m'arrête là?
Non, mais...
Au niveau du timing...
Non, continue un petit peu, Raphaël, avec plaisir.
Donc, ce que je voulais vous dire, c'est que l'électricité, c'est vraiment un vecteur clé de cette décarbonation. En France, on a une électricité qui est décarbonée, donc c'est une opportunité. Alors, il y a le nucléaire, mais il y a aussi les barrages hydrauliques. Il ne faudrait pas les privatiser ou les mettre sous gestion étrangère. Il vaut mieux qu'ils soient dans le service public français, géré par un opérateur français, parce que non seulement c'est une électricité qui est stockable, mais en plus qui est rentable. Et donc, pour le nouveau nucléaire, c'est vrai que l'EPR actuel de Flamanville a eu quelques déboires financiers et un petit peu de retard en termes de nombre d'années. Donc il faudrait vraiment maîtriser la filière. Donc quand on parle de souveraineté, il y a une notion aussi de compétences. Il n'y a pas qu'une notion de technologie et de ressources. Est-ce qu'on a les compétences et le capital humain pour lancer des grands chantiers, les maîtriser? Identifier les risques, ce n'est pas pareil que les maîtriser. Donc maîtriser les grands chantiers pour fabriquer de nouveaux réacteurs nucléaires. Et en termes de financement, alors on me dit toujours, oui, mais il y a un taux d'endettement de plus de 110% des pays européens. Il y a une disette budgétaire en France, il faut chercher 40 milliards d'économies. Donc je comprends tout ça, mais il y a aussi la notion de finances privées, d'allocation des ressources qui peut être faite différemment, du rôle des banques. Ce n'est pas interdit de faire appel aussi à la finance privée, de ne pas opposer toujours finance publique et finance privée. Et quand je discutais avec le président de l'IFPEN hier, lui essaye de porter une idée qui est intéressante aussi, c'est une sorte d'emprunt, de grand emprunt, au faveur de la transition écologique, justement dans cette idée de transmission et d'investissement pour les générations futures. Donc je pense que cette idée qui est portée par l'IFPEN est une idée intéressante aussi. Donc il y a des leviers, il faut juste éviter de changer de cap en permanence, parce qu'il n'y a rien de pire que le stop and go pour les industriels.
Merci beaucoup, Raphaël. Donc, visibilité, transparence, tenue de cap, stratégie, effectivement, financement, c'est essentiel si on veut réussir cette transition climat. Maria Georgiadou, merci beaucoup de nous rejoindre par Teams. Maria, vous êtes experte senior en politique de recherche et d'innovation sur les énergies renouvelables à la Commission européenne. Vous travaillez comme experte senior à la Direction générale de la recherche et de l'innovation. Vous pilotez l'orientation stratégique de la recherche et de l'innovation dans le domaine des carburants renouvelables, des biocarburants, de la bioénergie, ainsi que le développement et la mise en œuvre des programmes et politiques de recherche et d'innovation dans le cadre des programmes cadres de l'Union européenne. Vous êtes titulaire d'un doctorat et d'une maîtrise en génie chimique et d'un master en administration des affaires et aussi d'un master intégré en génie chimique. Donc Maria, sur ces enjeux de décarbonation, de défossilisation du secteur des transports, de façon plus générale sur ces enjeux de transition climat et énergie, quels sont les messages clés, quelles sont les recommandations que vous voulez partager aujourd'hui?
Thank you very much, Florence, for inviting me to this extremely interesting event that you organized today. I have to say, sorry that I have to switch the language because all the work I've been doing is in English. And my key messages here are that we cannot do without renewable fuels for decarbonizing our energy for transport in also a competitive way. We have particular targets for biofuels, advanced biofuels and biogases in transport for 2030, all types of transport, not just aviation and maritime, road transport as well. This is a very well-known 5.5% in 2030 advanced biofuels and biogas according to Annex 9, Part A of the RED 3. We have a particular target for RFNBOs, also 1% by 2030 in transport. And we have the ReFuelEU Aviation and FuelEU Maritime that are really based on renewable fuels for making the decarbonization for 2030 and 2050 with particular targets for bio and non-biological origin fuels. So, first, the policy in the EU recognizes the importance of these renewable fuels. Secondly, according to the work we have been doing in DG Research and Innovation for years, with the technologies and with the studies, we really identified that these solutions of the renewable fuels have a role to play, which is crucial for the reduction of the emissions in the transport sector, and they can contribute significantly to the Fit for 55 objectives and to the climate neutrality goals for 2050. This actually can fit the retardness of the other solutions for the decarbonization of transport, like the electrification. And as these technologies become more mature, the value chains become more established. The fuels can be commercialized, and then we can have commercial plants and then economies of scales with the replication. Then we will have more and more critical role of these renewable fuels into the transport sector. Now, I heard today various challenges with biomass, with efficiencies, and all this. It is true that the biomass as a feedstock is not unlimited, but based on studies that we have done with renewable universities in the EU, we identified that in the EU we do have domestic feedstocks according to Annex 9A and B parts that can fulfill the demand for 2030 and beyond, but we should go more to the increasing the biomass production of unused degraded lands and from intercropping and from cover crops as we go towards 2050. So this is another key messages for the biofuels. And if we do that, we will have quite an important environmental and socioeconomic impact, because the more the volumes we have, the more the greenhouse gas emission savings we will have, and particularly from the advanced technologies, which are the advanced biofuels and the RFN BOs. We do have progressed with LCAs. We have certification methods in place. There are 13 certification schemes. So this will help the uptaking of these technologies from the sustainability point of view. And also, since we have these biofuels at rural areas, the biomass is mostly at rural areas, and this will create a decentralized scenario. If we also have intermediate bioenergy carriers concepts developed, which will help the rural economy and also creates a lot of jobs along the entire value chain, and not just on the maintenance of the renewable energy generator. So with this in mind, and with in mind that we can create synergies between advanced biofuels production and RFNBOs production, we can also create net zero emissions and negative emissions, because biomass by itself has this inherited property to create negative emissions, so that the impact on the socioeconomic can be even higher. But I would say that we need to have a lot of support still, because technologies are not really yet commercial. So we need to support a lot with research and innovation, not only the low-hanging fruits, but also the emerging technologies. And then with appropriate market-based measures to try to pull these technologies and create a pipeline of technologies that they go to the market, and they produce continuously more and more efficient volumes of those renewable fuels. I think I will stop here.
Thank you. Sorry. Thank you very much, Maria. Je pense que maintenant nous allons prendre quelques questions de la salle. Est-ce qu'il y a des questions dans la salle? Jean-Baptiste.
Une question pour notre intervenant en économie. Comment vous voyez le rôle des États dans le fléchage des ressources, que ce soit la biomasse ou les térawattheures, de manière à éviter des conflits d'usage et une imbalance de l'offre et de la demande trop importante?
Je vous remercie pour cette question. Effectivement, le problème, c'est qu'il y a un défaut d'État stratège, et donc c'est important, quand il y a un conflit éventuel en termes de ressources, de voir comment il faudrait faire. Et donc c'est vrai qu'il faudrait peut-être un retour à une vraie planification, comme on a pu connaître, qui a pu faire naître justement le programme nucléaire sous le gouvernement Mesmer. Et donc l'idée, on en parlait avec Valérie Demangel hier soir, c'était de faire des études, tu disais, de coûts, bénéfices, compétitivité de différentes technologies, pour voir à partir d'études fiables où est-ce qu'il faudrait orienter les ressources, parce que vous avez entièrement raison, il n'y a pas de problème vraiment de, enfin, à moins que je me trompe, mais de ressources financières, mais vraiment une question d'allocation de ressources financières. Et donc c'est vrai que quand on voit que, par exemple, le coût de l'électricité est un facteur déterminant, et qu'hier on a rappelé qu'il y avait un écart entre zone US et Europe de coût de l'électricité 2 fois plus élevé en Europe, on se dit qu'il va falloir vraiment peut-être aller plus loin dans la réforme du marché européen, notamment pour qu'il y ait un lien plus direct entre coût de production d'électricité et puis prix de l'électricité sur le marché européen, prix de gros. Et donc, par rapport à ça, il faut absolument mettre en place ces mécanismes-là pour avoir une visibilité sur le prix de l'électricité pour les industriels, ce qui résonne de manière assez simple finalement, ils ont raison, c'est de dire qu'ils vont ouvrir les usines là où le coût de l'électricité sera le plus faible, enfin un ensemble de coûts, mais celui aussi de l'énergie, qui représente pour notamment les électro-intensifs 30 à 40% de leur coût de production, donc c'est non négligeable. Et donc pour ça, il faut avoir un prix qui reste stable et sur lequel on a une visibilité.
Merci. Est-ce qu'on a une autre question dans la salle? Valérie? Valérie puis Nicolas.
Une précision par rapport à ce que disait Raphaël. Moi, j'étais plus sur l'évaluation en fait du bénéfice de la techno en termes de décarbonation, c'est-à-dire l'efficacité de la techno. Combien de décarbonation, mais au sens large, pas que pour la mobilité. Hein. Donc, qu'est-ce qu'on sort comme CO2 de l'atmosphère avec les technos, en fait? Et donc, est-ce que ce n'est pas une priorité de subvention sur les technos qui vont sortir massivement, enfin, qui vont être le plus efficaces pour sortir du CO2 de l'atmosphère? Mais il faut faire des analyses complètes, c'est-à-dire que on ne va pas, par exemple, Raphaël parlait d'électricité nucléaire, on ne va pas faire l'analyse sur le fait uniquement qu'on produit en France et qu'elle est décarbonée. Il faut aussi regarder tout ce qu'on importe ailleurs. Et puis moi, je ne crois pas personnellement au développement massif des mines sur nos territoires pour des raisons d'acceptabilité. Ça sera très, très, très compliqué. Donc, on voit bien dès que c'est not in my backyard. Hein. En Europe, beaucoup se verraient bien dans un désert, malheureusement, où il n'y a plus de CO2, mais où on ne produit plus. Je crois que chacun individuellement est peu prêt à accepter des industries près de chez soi. Donc le sujet, il est déjà là. Bon, enfin, donc en tous les cas, l'intérêt serait d'évaluer le potentiel de décarbonation de chaque techno et peut-être d'aller au plus efficace. C'est juste pour préciser un peu l'échange.
Oui, je partage tout à fait, Valérie. Et puis après, il y a le potentiel de décarbonation, et puis après, il y a tous les effets connexes, en fait, qui sont aussi importants, parce que des fois, il y a des solutions. Ça peut être sur la partie métaux ou autres, besoins en eau, ou des choses comme ça, qui sont aussi extrêmement importants. Sylvain?
Oui, bonjour. Ma question s'adresse en particulier à Maria Georgiadou à distance. Do you want me to ask a question in English, or is it okay for French?
Oui.
English? Yeah.
I cannot hear very well, so first one thing is the acoustics, and then yes, please go in English.
In English, okay. So
and the micro is a problem.
You raise your hand if you cannot hear me properly, okay? I work for Bioéthanol France. We represent the producers of bioethanol in France. So as you know, France is the first producer, 20% of production in Europe. But Europe is very little compared to the rest of the world. We know that. We produce about 80% from 1G directly and 20% from processing residues from the starch industry and the sugar industry. And the performance of the production in France is quite good. I can give some example here near Lac. We have a 1G corn-based ethanol production, and the GSG saving is around 80% with 1G. And we also have a member using residues in northeast of France, and his performance is above 100% reduction. Because as you know, we have capture of CO2, and that capture of CO2 is a big improver also for the performance. My question is, regarding Annex 9 and non-Annex 9 feedstock. Science from the European Commission studies in 2019 has shown that the difference is between those biofuels that produce directly deforestation and those who do not. There is this study that has demonstrated that there is high hydraulic risk with palm oil and possibly with soy as well, but the rest of the crops are more or less immune in most of the world. So isn't it time to differentiate the biofuel, not between 1G and the rest, but between those who deforest and the rest, and give chance to some increased production and consumption on 1G alongside the development of new technologies? Because sometimes, you need to bet on things that work already and not bank only on things that are entirely new. So decarbonization needs real solutions that work. So, if you can use more 1G that doesn't deforest, it's good to have it and also to invest on the new technologies that is, let's say, more risky in terms of industrialization. So do you agree that we should have, let's say, a different focus, not excluding developments in 1G, whereas we continue to invest in new technologies that are, let's say, more expensive and more risky, but may, at the end, provide some solution as well?
Thank you for your question. Although my field is not really the policy, I can give you the opinion that I have this. The ILUC notion exists in RED 3. So the low ILUC still exists. And as you say, the high ILUC are excluded and they are going completely to be removed from the subsidies by 2030. It will go to zero, but the others that are low ILUC biofuels remain. So the advances that one can have in this low ILUC biofuels are for sure interesting, because as I said in the beginning, we will need all the resources of sustainable biofuels to meet the carbons. We now expand to degraded lands and to severely contaminated lands in order to fulfill the demand created first in aviation and then also from the residues and the other waste-based biofuels to go to the other sections as well. Another thing is that you could combine the CO2 which is produced from this low ILUC biofuel production and make RFNBOs. The RFNBOs do not distinguish whether the CO2 is of bio or non-bio origin. They say that the energy, the renewable energy that enters, the energy that enters in the production should be of renewable. And the energy carrier here is the hydrogen and not the CO2. So combining this kind of production, you could also provide a way of a source of CO2 to make RFNBO. So I really, from the technological point of view, like the advances of new technologies and of solutions that can provide kind of more availability and more affordability of these new technologies in the market.
Thank you, Maria. Raphaël, you want to...
Oui, non, moi ce que je voulais dire, c'est que effectivement la notion de neutralité technologique elle est très importante parce que si le politique décide de la technologie, au lieu de fixer simplement un cap en disant il faut décarboner à hauteur de par exemple 0,55%, on laisse aux industriels le choix technologique et on ne se retrouve pas avec des interdictions comme celle de 2035 des véhicules neufs thermiques en Europe, en se rendant compte que finalement, pour des voitures électriques, on a besoin des minerais ou des terres rares venant notamment de Chine, qui a un quasi-monopole à la fois sur les ressources, mais aussi sur la chaîne de valeur, le raffinage des ressources et puis les technologies actuelles et futures des véhicules électriques, parce qu'ils ont un grand marché, donc ils peuvent amortir toute leur R&D sur leur marché intérieur et ils peuvent jouer à la hausse comme à la baisse sur les cycles de prix des minerais. Donc quand je l'avais dit il y a quelques années, on m'avait dit non, que ça n'arriverait pas, que ce n'était pas dans l'intérêt de la Chine. Bon, j'avais simplement rappelé qu'ils avaient interdit l'exportation de minerais au Japon en 2010 et que là, ils viennent de restreindre leur exportation il y a quelques jours aussi, dans une optique de faire jouer les prix et puis d'avoir un rapport de force, notamment avec les Américains. Donc, c'est bien de prendre des décisions dans l'intérêt de la décarbonation, mais il faut avoir des études d'impact et un plan d'anticipation par rapport à ce qui est nécessaire pour les atteindre, sachant qu'effectivement, la décarbonation est source à la fois d'attractivité et de compétitivité des filières industrielles européennes à venir.
Merci, Raphaël. Ah, on a encore un petit peu de temps? Oui, donc Maxime.
It is switch. Okay. We've discussed extensively the potential solutions to reach net zero by 2050. And for me, the solutions is always to decrease in absolute value these solutions. So we haven't mentioned sobriety, like sufficiency today. And how do you think it is integrated in the current regulation or could be integrated to catch the human behavior and the rebound effects potentially associated with these technological evolutions?
Maria, do you want to take this one or do you want me to go?
Okay, I will try to answer that when the regulation is made, the social impact is also analyzed in the impact analysis before the regulation. Now, for sure, the areas of energy poverty, how this is going to be impacting the households, etc., has been analyzed before all the regulations of energy-related and climate-related policy were released. Now, if it is ideal, this I'm not in a position to judge, but I can confirm that there is goodwill to go towards helping the society for the climate, for the economy, for the environment, and not going against it. So there is public consultation also before every legislation and regulation, and these opinions of the public, when they are reported, are also analyzed and taken into account.
And maybe if I can just follow up a little bit, it was also mentioned yesterday, but you can also find there is like the Smart, Sustainable and Mobility Plan, and in that plan released by the European Commission, you will find different recommendations to increase the mobility, like cycling and pedestrian mobility in the cities, and also to develop the rail as well. So you have a lot of incentives and also a lot of ideas to go, I believe, in the direction that you mentioned, to maybe meet more sobrieties, especially both in cities and also in peri-urban areas. So you have some, you can find some material on the European website.
Merci. Et juste pour préciser à nos collègues, donc effectivement, il y a eu des déclinaisons en France que tu ne connais, Maxime, qui sont les scénarios de l'ADEME, dans lesquels effectivement il y a des scénarios très très stricts en termes de sobriété. Il y a 4 scénarios avec différents niveaux qui sont quand même des guides qui permettent de voir ce qui est possible aussi, parce qu'il y a aussi ces enjeux de justice sociale qui sont aussi extrêmement importants. Je pense qu'on a débordé et je vous prie de m'en excuser. Mais
je pense qu'on va en effet remercier le comité scientifique, s'est regroupé. Quelques applaudissements. Merci beaucoup. Merci. Pour toutes ces personnes. Je vais inviter Valérie Demangel maintenant à me rejoindre, directrice de mission Europe et internationale, et bien sûr également à l'organisation de cet événement pour ces quelques mots de conclusion.
Je crois que vous avez tous envie d'aller déjeuner sur le balcon. Certains ont prévu une visite à 14h à l'usine de Vertex. Donc vous allez voir en grandeur réelle le site. Oui, alors ceux qui sont intéressés, vous manifestez auprès de Nicolas et Sylvain pour l'organisation des transports. Donc voilà, moi je veux juste remercier l'ensemble des protagonistes du forum, que ce soit hier ou aujourd'hui. Merci, une mention particulière au comité scientifique. C'est beaucoup de travail depuis le mois de janvier. Donc on a effectivement innové avec ce nouveau format. Je crois qu'il y a beaucoup encore de choses à dire et d'opinions à confronter. Ce sujet est vaste, celui de la transition. Et ce dont on est tous sûrs aujourd'hui, c'est que collectivement, nous souhaitons avancer vers la décarbonation en prenant en compte évidemment le besoin de souveraineté de notre Europe. Mais il y aura certainement un déclencheur fort dans les années à venir qui sera l'Europe de la défense. Donc à très bientôt pour une nouvelle édition, probablement plutôt dernier semestre 2026 à Pau. Et merci encore à vous tous. Merci. Thank you very much. Maria, see you. Bye. Thank you.
Thank you. Bye-bye.
Merci beaucoup. Ainsi se conclut donc la 4e édition de ce Forum européen des mobilités bas carbone. Se conclut uniquement le forum. On voit que les échanges, eux, vont se poursuivre encore. Merci à la communauté d'agglomération Pau Béarn Pyrénées. Merci aux différents partenaires, Terega, IFPEN Énergie Nouvelle, Nacre, Bioéthanol France. Merci également pour toutes les équipes du Tour d'Europe. Donc, comme on le précisait il y a quelques instants, on va vous donner les modalités pour la visite de l'usine de raffinerie Vertex d'ici à quelques instants. Merci aux équipes de Créa Sud Communication. Bonne journée à toutes et à tous.